Hello and welcome to Space Historians. I'm so glad you have joined me tonight, ready to let go of the day's momentum and drift gently into something larger, something quieter, something that stretches beyond the everyday concerns that fill our hours. Tonight, we are going to explore a question that sounds simple but opens into vastness. How far does our galaxy actually reach? Not the distance to another galaxy, not the span of the universe, but the extent of our own home among the stars, the Milky Way itself. Before we begin this journey, I would love to know, where are you listening from right now? What time is it in your corner of the world? Perhaps evening is settling in around you, or perhaps it is already deep into the night. Maybe dawn is approaching, or maybe you are somewhere in between, in that quiet hour when the world feels suspended. It always amazes me that people from different time zones, different continents, different skies above them, can all be here together in this moment, sharing the same curiosity about the cosmos. The Milky Way stretches above all of us, though we each see it from our own unique angle. If you find these quiet explorations helpful, a like or a subscribe helps this channel continue, helps these calm journeys reach others who might need a gentle voice and vast perspective to carry them towards sleep. For those who have already joined this constellation of listeners, thank you. You are part of this voyage. Tonight's journey is about boundaries that are not really boundaries at all, about edges that fade rather than stop, about a home so vast that measuring it requires rethinking what we mean by distance itself. We live inside the Milky Way. We are not outside looking in, but inside looking across, and that changes everything about how we measure it, understand it, and define where it ends. So as your breathing begins to slow, as your body settles into stillness, imagine standing beneath a truly dark sky, far from city lights. That hazy band arching overhead is not decoration. It is the cross-section of your galactic home, billions of stars so distant they blur into a single sweep of light. But how far does that home extend? Where does it stop being the Milky Way and start being the space between galaxies? That is what we will explore together, gently, slowly, with room for wonder and rest. Let us travel together through the layers of our galaxy, from the bright disk we can see to the invisible halos that stretch into the cosmic dark, from the spiral arms near us to the faint streams of stars at the very edge of belonging. Welcome to the quiet side of understanding. Welcome to the edge of home. There is something peculiar about trying to measure the place you live. If you want to know how big a city is, you can climb a hill outside it and look back, see where the buildings end and the countryside begins. If you want to know how large an ocean is, you can view it from space, trace its shorelines, calculate its area. But if you want to know how far your galaxy reaches, you face an impossible challenge. You are inside it, looking across it, trying to map something vast while standing in the middle of it. This is not a small problem. It is the fundamental difficulty that has shaped 3 centuries of astronomy. We cannot step outside the Milky Way to photograph it from above. We cannot fly to another galaxy and look back. We are embedded within the structure we are trying to understand, like a person standing in the middle of a forest trying to determine where the trees end. And yet, despite this limitation, we have learned extraordinary things. Through patience, through clever measurements, through the slow accumulation of data, astronomers have built a picture of the Milky Way's extent. Not a perfect picture, not a complete one, but a picture detailed enough to inspire awe. The impossibility is what makes the achievement remarkable. We have measured distances we cannot travel. We have traced structures we cannot see directly. We have inferred the presence of matter we cannot detect except through its gravitational pull. All from our single vantage point, embedded in one spiral arm, 27,000 light-years from the centre, looking outward through dust and gas that obscure much of the view. When you look up at the night sky from a truly dark location, you can see that band of light stretching across the heavens. The ancient Greeks called it the Milky Circle, Galaxias Kyklos, from which we derive our word galaxy. To them, it appeared as spilled milk across the darkness, hence Milky Way. They did not know what it was, only that it looked different from the scattered stars around it. For most of human history, that band was a mystery. Some cultures saw it as a river, others as a path of spirits. still others as a backbone holding up the sky. The truth, when it was finally understood, turned out to be stranger and more wonderful than any myth. The band is not something separate from the stars. It is stars, countless billions of them, so distant and so numerous that they blend into a continuous glow. We are seeing the Milky Way from inside, looking along the flat disk in which most of its stars reside. When we look toward the band, we are looking through the densest concentrations of stars. When we look above or below the band, we are looking out of the disk into the emptier space beyond. This realization, obvious to us now, took centuries to establish. It required telescopes to resolve some of the glow into individual stars. It required careful mapping to show that the stars were not scattered randomly but arranged in patterns. It required measurements of distance to prove that the structure extended far beyond the solar system. The impossibility of our situation means that we must work indirectly. We cannot measure the Milky Way's width with a ruler. We must identify stars of known brightness and calculate how far away they must be to quickly appear as faint as they do. We cannot see the spiral arms directly from above. We must map the positions of young stars and gas clouds and infer where the arms lie. We cannot photograph the dark matter halo. We must measure the speeds of stars orbiting at different distances and deduce how much unseen mass must be present to keep them moving as they do. Every measurement is a chain of inference, each link introducing uncertainty. And yet the chains hold. Multiple independent methods converge on similar answers. The picture that emerges is consistent, tested, refined over decades of observation. We may be standing in the middle of the forest, but we have learned to map it nonetheless. The scale of what we are trying to measure adds another layer to the impossibility. The Milky Way is not just large. It is immense beyond ordinary comprehension. Light, travelling at 300,000 kilometers per second, takes 100,000 years to cross from one side of the visible disk to the other. That is the span we are trying to understand from our single point within it. And the visible disk is only part of the story. Surrounding it is a halo of old stars and globular clusters extending twice as far. Beyond that, a halo of dark matter reaching perhaps 10 times farther still. The galaxy we can see is embedded in a structure vastly larger, most of it invisible, detected only through its gravitational effects. So when we ask how far the galaxy reaches, we are asking multiple questions at once. How far do the stars extend? How far does the gas? How far does the dark matter? Where does the Milky Way's gravitational influence end and the influence of neighbouring galaxies begin? Each question has a different answer, and none of the answers are sharp lines. They are gradients, regions where one thing fades into another. The impossibility is also temporal. We see distant parts of the galaxy, not as they are now, but as they were when their light began its journey toward us. A star 10,000 light-years away appears to us as it looked 10,000 years ago. The galaxy we see is a patchwork of different moments, all arriving simultaneously at our eyes, creating an image that is both real and historical, current and ancient. Despite all these challenges, the attempt to measure our galaxy has become one of the great projects of modern astronomy. It has driven the development of new instruments, new techniques, new ways of thinking about distance and structure. It has taught us that our home is far larger than we imagined, that most of it is invisible, that its boundaries are not boundaries at all but transitions into something else. Tonight, as you settle into stillness, think about this impossible task. From one point inside a vast structure, we have learned to measure it, to map it, to understand its shape and extent. The achievement is a testament to human persistence, to the power of indirect reasoning, to the willingness to ask questions that seem unanswerable. The Milky Way stretches around us in all directions, fading gradually into the darkness between galaxies. We cannot step outside to see it whole, but we can piece together its story from fragments of light, from the motions of stars, from the pull of invisible matter. The impossibility is what makes the quest beautiful. We reach toward understanding, even when the view is obscured, even when the distance is vast, even when we are trying to measure the very space in which we exist. And from that impossibility, from that patient accumulation of knowledge, we have learned something profound. Our galaxy is both immense and intimate. It stretches farther than light can travel in a human lifetime, yet we are part of it, embedded in its structure, made of its matter. The impossibility of measuring it from within is also the privilege of belonging to it, of calling it home. Long before anyone knew what a galaxy was, people noticed the band of light stretching across the night sky. They looked up from every continent, every culture, every era of human history, and they saw it. That faint, luminous streak, arcing from horizon to horizon, persistent and mysterious, demanding explanation. The ancient Greeks called it galaxias, the Milky Circle, because it looked like spilled milk painted across the darkness. They wove stories to explain it. Some said it was milk from the goddess Hera, sprayed across the heavens when the infant Heracles nursed too vigorously. Others imagined it as a road for the gods, a pathway between the mortal world and Olympus. In China, it was called the Silver River. Tianhe, a celestial waterway separating lovers in one of their most enduring myths. In India, it was the path of the gods, Akash Ganga, the heavenly Ganges. Indigenous peoples of the Americas saw it as the road of souls, the path spirits travelled after death. The Kalahari people of southern Africa called it the backbone of night, holding up the sky. Every culture that looked up and wondered created their own story, their own way of making sense of that soft glow, but none of them knew what it truly was. They saw the effect without understanding the cause. They recognized the pattern without grasping the structure. The first person to look at the Milky Way through a telescope and understand that it was made of stars was Galileo Galilei. In 1610, shortly after constructing one of the earliest astronomical telescopes, he turned it toward that hazy band and saw something astonishing. The blur resolved into countless individual points of light. Where the naked eye saw only a smudge, the telescope revealed stars, thousands upon thousands of them, too distant and faint to be distinguished without aid. Galileo described what he saw in his book Sidereus Nuncius, the Starry Messenger. He wrote that the Milky Way was nothing but a congeries of innumerable stars distributed in clusters. It was a revolutionary observation, one that began to shift, understanding from myth to measurement, from story to structure. But even Galileo did not know what he was looking at, not really. He saw that the Milky Way was made of stars, but he did not know it was a galaxy. The concept of a galaxy, of a vast island of stars separate from others, would not emerge for centuries. To Galileo and his contemporaries, all the stars they could see, whether in the Milky Way or scattered across the rest of the sky, were simply the stars. There was no notion of them being organized into a larger structure, no understanding of scale beyond what could be measured within the solar system. The question of what the Milky Way was continued to puzzle astronomers for generations. Some proposed that it was a flattened distribution of stars, with our sun somewhere inside. Others thought it might be a nebula, a cloud of glowing gas. Still others suggested it was simply a concentration of stars in one direction, with the sun at or near the centre of the universe. In 1750, Thomas Wright published a speculative work suggesting that the Milky Way was a flat layer of stars and that the sun was embedded within it. His ideas were not widely accepted at the time, but they pointed in the right direction. He imagined the stars arranged in a thin disk, and when you looked along the plane of that disk, you saw the concentrated glow of the Milky Way. When you looked perpendicular to the disk, you saw fewer stars and darker sky. A few years later, Immanuel Kant, the philosopher, read about Wright's ideas and took them further. Kant proposed that the Milky Way was a rotating disk of stars held together by gravity, and that similar structures might exist elsewhere in the universe. He called them island universes, separate systems of stars like our own, scattered through the vastness of space. It was a visionary idea, decades ahead of its time, though Kant had no way to prove it. The first person to systematically map the Milky Way was William Herschel. In the late 1700s, using powerful telescopes he built himself, Herschel counted stars in different directions across the sky. He assumed that all stars had roughly the same intrinsic brightness, which meant that fainter stars were farther away. By counting how many stars he could see in each direction, he could estimate the shape and extent of the stellar system. Herschel concluded that the Milky Way was indeed a flattened disk, with the Sun near the centre. His maps showed the disk extending much farther in the plane of the Milky Way than perpendicular to it, confirming the basic geometry. But his measurements were limited by the fact that he could not account for dust. The interstellar medium absorbed starlight, making distant stars appear fainter than they were. This caused Herschel to underestimate distances and place the Sun too close to the centre. Still, his work established the foundation. The Milky Way was not a random scattering of stars, but an adeptly organised structure, a disk with a definable shape. That realisation was the beginning of mapping our galactic home. The question of where it all began is not just about ancient myths or early telescopes. It is about the long, patient process of noticing, wondering, measuring, and refining. Each generation of astronomers built on the work of those before them, adding details, correcting errors, pushing the boundaries of knowledge outward. By the 19th century, the basic shape of the Milky Way was understood. It was a disk, and we were inside it. But the size of that disk, the number of stars it contained, and whether other such systems existed beyond it, remained unknown. The tools were not yet precise enough. The methods were not yet refined enough. The data were not yet sufficient. What kept astronomers going was the simple fact of the band in the sky. It was there every clear night, unchanging, patient, waiting to be understood. And slowly, through centuries of observation, its nature revealed itself. Not all at once, not through a single breakthrough, but through accumulation. Each measurement added a piece. Each telescope improved the view. Each theory refined the framework. The story of where it all began is also a story about perspective. For most of human history, we thought we were at the centre of everything. The Earth was the centre of the solar system. The Sun, once displaced from that position, was thought to be near the centre of the universe. The Milky Way, when recognised as a structure, was assumed to contain everything. Each of these assumptions was wrong, and each was corrected through observation. We are not at the centre of the solar system. We are not at the centre of the Milky Way. The Milky Way is not the universe. Each shift in perspective expanded our sense of scale, pushed our understanding outward, reminded us that the cosmos is larger than we imagined. But those shifts did not happen quickly. They required patient work, careful measurement, and the willingness to question assumptions. The band of light that stretched across the sky was the same for ancient observers and modern ones. What changed was not the sky, but our ability to interpret it. As you rest now, breathing slowly, think about those early observers standing beneath the same stars we see today. They noticed the band, wondered about it, created stories to explain it. They did not have telescopes or mathematics, but they had curiosity. That curiosity, passed down through generations, eventually led to understanding. The Milky Way has been there all along, unchanged across millennia of human history. What changed was us. Our tools, our methods, our willingness to look carefully and think deeply. The beginning was not a single moment, but a long process of paying attention, of refusing to accept mystery as the final answer, of building knowledge slowly across centuries. And from that beginning, from those first telescopic observations and early maps, we began to grasp the true nature of our galactic home. Not a decoration in the sky, not a myth painted across darkness, but a vast physical structure, a disk of stars extending far beyond what our eyes alone could reveal. The story had begun. Now it would take centuries more to understand just how far that structure reached. The real breakthrough in understanding the Milky Way came not from looking at it directly, but from looking at something else entirely. In the early 1900s, astronomers were puzzling over faint, fuzzy patches scattered across the sky. They called them nebulae, from the Latin word for clouds, because that was what they looked like through telescopes. Soft, diffuse glows that did not resolve into sharp points like stars. Some nebulae were clearly within our own stellar system. They glowed with the light of nearby stars, or they were dark patches where dust blocked starlight. But others were different. They had a spiral structure, like pinwheels, with arms curving outward from a central hub. These spiral nebulae were mysterious objects, and astronomers debated fiercely about what they were. One camp, led by Harlow Shapley, argued that spiral nebulae were part of the Milky Way, perhaps small clouds of gas and dust within our own system. The Milky Way, in this view, was vast, perhaps the entire universe. Everything visible in the sky belonged to it. The other camp, led by Heber Curtis, argued that spiral nebulae were separate galaxies, island universes, as Kant had imagined, far beyond the boundaries of the Milky Way. If this were true, then the universe was incomparably larger than anyone had thought, filled with countless galaxies, each containing billions of stars. The debate came to a head in 1920 in what became known as the Great Debate, held at the Smithsonian Institution in Washington. Shapley and Curtis presented their arguments before an audience of astronomers and scientists. Both sides had evidence. Both sides had logic, but neither could definitively prove their case. The question remained open. The answer came a few years later, not from debate but from measurement. Edwin Hubble, working at the Mount Wilson Observatory in California with the largest telescope in the world at that time, turned his attention to the Andromeda Nebula, one of the brightest spiral nebulae in the sky. Using long photographic exposures, Hubble identified individual stars within Andromeda. Among them, he found Cepheid variables, pulsating stars whose brightness changes in regular cycles. The period of a Cepheid's pulsation is directly related to its intrinsic luminosity. By measuring the period, you know how bright the star truly is. By comparing that to how bright it appears, you can calculate its distance. Hubble measured Cepheids in Andromeda and calculated their distances. The result was stunning. Andromeda was not thousands of light years away, as Shapley had argued. It was hundreds of thousands of light years away, far beyond any estimate of the Milky Way's size. Later refinements would push that distance even farther, to over 2 million light-years. This single measurement changed everything. Andromeda was not part of the Milky Way. It was another galaxy entirely, separate and distant. And if Andromeda was a galaxy, then so were the other spiral nebulae. The universe was not just the Milky Way, it was a cosmos filled with galaxies, each one an island of stars scattered across unimaginable distances. The implications for understanding the Milky Way were profound. If Andromeda was a galaxy, and if it contained billions of stars arranged in a spiral disk, then the Milky Way must be similar. We were not looking at the universe from a central position. We were inside one galaxy among many, seeing our own structure from within. This realization sparked a new urgency to map the Milky Way accurately. If other galaxies could be photographed and studied from outside, their structures revealed clearly, then perhaps we could infer what the Milky Way looked like by comparison. But we still faced the fundamental problem. We were inside it, looking across it, unable to see the overall shape directly. The spark of mystery was not just about discovering other galaxies, it was about recognizing what that discovery meant for understanding our own. The Milky Way was not unique. It was one example of a type, a spiral galaxy, and by studying others we could learn about ourselves. Astronomers began comparing the Milky Way to external spirals like Andromeda and the Whirlpool Galaxy. They noticed patterns. Spiral galaxies had flat disks, central bulges, and arms where young stars clustered. They rotated, with stars orbiting the centre in ordered paths. They contained both old and young stars, gas and dust, regions of active star formation. The Milky Way showed these same features when observed from within. The band across the sky was the edge-on view of a flat disk. The concentration of stars toward the constellation Sagittarius marked the direction of the galactic centre. Young stars and gas clouds traced spiral arms, though seeing the full pattern was difficult from our position inside. The mystery began to resolve. The Milky Way was a spiral galaxy, probably similar in structure to Andromeda, though perhaps smaller. We lived in the disk, about 2/3 of the way out from the centre. The band we saw was simply the view along the plane of that disk, where stars were most concentrated. But understanding the type of structure we lived in was only the beginning. The real questions remained. How large was the Milky Way? Where did it end? How many stars did it contain? How did its mass distribute across space? These questions required more than comparison. They required measurement, and measurement from inside a structure is always difficult. The spark of mystery also ignited new methods. If we could not see the Milky Way from outside, we had developed ways to map it from within. Radio astronomy emerged as a crucial tool. Gas clouds emit radio waves that pass through dust, allowing astronomers to trace the spiral arms even where optical light is blocked. Infrared observations revealed stars near the galactic centre, hidden from visible telescopes by intervening material. Each new wavelength of light opened a new window. Each new technique added detail. The Milky Way began to emerge, not as a simple band of stars, but as a complex, layered structure with a disk, a bulge, a halo, and possibly a bar at the centre. The spark of mystery had ignited a century of discovery, a slow unveiling of the galaxy we call home. The realization that we lived in one galaxy among billions also shifted the question of edges. If galaxies were discrete objects, separate from one another, then they must have boundaries. But where were those boundaries? Did they stop sharply, or did they fade gradually? Did the Milky Way have a clear edge, or did it simply thin out until its stars merged with the emptiness of intergalactic space? These questions were not just academic. They touched on something fundamental about identity and belonging. If our galaxy had no sharp edge, then what did it mean to be part of it? Where did the Milky Way end and the rest of the universe begin? The spark of mystery, lit by Hubble's measurement of Andromeda's distance, had grown into a flame. It illuminated not just other galaxies but our own. It showed us that we were part of a larger cosmos, that our home was one among many, and that understanding its extent would require patient work across generations. As you sink deeper into rest, this moment in history settle over you. The moment when humanity realized the universe was far larger than anyone had imagined, when a single measurement of distant stars revealed that our galaxy was not everything, that it was one structure among countless others. The spark had been struck. Now, the work would begin to trace the full extent of our galactic home, to map its boundaries, to understand how far it truly reached. When Hubble's measurements proved that Andromeda was a separate galaxy far beyond the Milky Way, the astronomical community responded with a mixture of wonder and resistance. The implications were simply too vast to absorb immediately. Everything astronomers thought they knew about the scale of the universe had to be reconsidered. Harlow Shapley, who had argued so forcefully that spiral nebulae were part of the Milky Way, found himself facing a difficult moment. He had been wrong about something fundamental. The Milky Way was not the entire universe. It was merely one galaxy among what would eventually be recognized as hundreds of billions. The cosmos had expanded overnight, not physically, but in human understanding. Shapley's initial reaction was reportedly one of skepticism. He questioned Hubble's measurements, wondered if there might be errors in the Cepheid calibrations, suggested alternative explanations. This was not stubbornness, but the natural response of a scientist whose framework had been challenged. In science, extraordinary claims require extraordinary evidence, and the claim that the universe contained countless galaxies was extraordinary indeed. But the evidence accumulated. Hubble found more Cepheids in Andromeda, measured more distances, and extended the technique to other spiral nebulae. Each measurement confirmed the same conclusion. These were not small nearby objects. They were enormous distant systems, each containing billions of stars. The evidence became overwhelming. Gradually, even the skeptics accepted the new reality. Shapley himself, though disappointed that his model had been wrong, adapted to the new understanding. He continued his own important work, measuring the scale of the Milky Way and mapping the distribution of globular clusters. His willingness to accept evidence that contradicted his beliefs demonstrated the strength of the scientific method. Ideas must yield to data, no matter how elegant or strongly held those ideas might be. For many astronomers, the expansion of the known universe was not disorienting but exhilarating. If there were billions of galaxies, each one a vast system of stars, then the universe was far richer and more complex than anyone had imagined. The Milky Way, though no longer unique, was still our home. Understanding it became more urgent, not less, because now we could compare it to others, learn from the patterns visible in external galaxies, and apply those lessons to mapping our own. The public reaction, when news of the discovery filtered beyond scientific circles, was equally mixed. Some people felt a sense of cosmic loneliness. If our galaxy was just one among countless others, did that make humanity even more insignificant than we had already seemed? The Earth was a small planet circling an ordinary star in the suburbs of a typical galaxy. How could human life matter in such an immense cosmos? Others felt the opposite. The vastness of the universe, far from diminishing human significance, elevated it. We were the beings capable of understanding this vastness, of measuring distances we could never travel, of comprehending scales beyond ordinary experience. That capacity for knowledge was itself remarkable, a sign that consciousness, however rare, could reach across the cosmos with thought, even when it could not reach with hands. The newspapers of the 1920s ran headlines about the expanding universe, though they often conflated Hubble's discovery of external galaxies with his later work showing that those galaxies were receding from us. The public imagination seized on the idea of an infinite cosmos, of endless possibilities, of other worlds and perhaps other intelligences scattered across the galaxies. For astronomers, the awe was tempered by practical concerns. If the Milky Way was one galaxy among many, then measuring its extent became both easier and harder. Easier because we could now observe other spiral galaxies and infer that our own had similar structure. Harder because we still could not step outside to see it directly, and the comparisons were only approximate. The question of how far the Milky Way reached took on new dimensions. External galaxies showed clear disks, but they also had faint outer regions and halos of stars extending beyond the bright spiral arms. Did the Milky Way have similar features? How far did those faint outer regions extend? Were they part of the galaxy proper, or were they something separate? Another source of wonder was the realization that light from Andromeda took over 2 million years to reach Earth. When we looked at Andromeda, we saw it as it was 2 million years ago, long before human beings existed. The light that entered our eyes tonight had been travelling since a time when our ancestors were not yet human, when the evolutionary path that would lead to us was still unfolding. This temporal dimension added to the awe. The universe was not just vast in space, but also in time. Every observation was a look into the past, and the farther we looked, the deeper into history we peered. The Milky Way itself, viewed from Andromeda, would appear as it was 2 million years ago. An observer there would not see our present but our ancient past. The disbelief gradually gave way to acceptance, but the sense of awe never faded. Each new measurement, each new galaxy catalogued, each refinement of distance scales added to the picture of a universe almost incomprehensibly large. And yet, within that universe, the Milky Way was our anchoring point, our frame of reference, the one galaxy we could study in detail. Astronomers began to ask new questions. If galaxies were common, how did they form? Why did they have the structures they did? What determined their sizes and shapes? The Milky Way became not just an object of study in itself, but a laboratory for understanding galactic physics generally. The awe also came from recognizing the achievement. Humans, confined to one small planet, had reached out with instruments and mathematics to measure structures millions of light years away. We had determined that spiral nebulae were galaxies, calculated their distances, and begun to understand their nature. The fact that this was possible at all seemed almost miraculous, and the implications for understanding the Milky Way were profound. If we could measure the distances to other galaxies, we could also measure the distances to objects within our own. The same techniques that revealed Andromeda's distance could map the extent of the Milky Way. Cepheid variables, for instance, existed in our galaxy too, and by measuring their distances, we could trace the structure of the spiral arms. The disbelief that accompanied Hubble's discovery was not about rejecting evidence, but about adjusting to a new scale. The universe had suddenly become vastly larger, and that required rethinking everything. Where did the Milky Way fit in this new cosmos? How did it compare to other galaxies? What could we learn about it by studying them? As you breathe slowly now, let the wonder of that moment wash over you. Imagine being an astronomer in the 1920s, realizing that the faint smudge visible through a telescope was actually an entire galaxy, a system of billions of stars, separated from us by a gulf so vast that light took millions of years to cross it. The universe had revealed itself to be far larger than anyone had dreamed. And the Milky Way, our home, was just one small part of that vastness. The awe and disbelief were natural responses to a discovery that reshaped our understanding of existence. But they were also the beginning of a new era. An era in which the question of how far our galaxy reaches could be asked with new tools, new methods, and new perspectives drawn from observing the cosmos beyond our borders. Once, astronomers accepted that the Milky Way was a galaxy comparable to others they could observe. A strange contradiction emerged. When you look at a photograph of a spiral galaxy like Andromeda or the Whirlpool galaxy, you see a clear structure. Bright central bulge, sweeping spiral arms, a defined disk that fades at the edges. The boundaries are not sharp, but they are visible. You can point to the photograph and say, there is where the galaxy is bright, and there is where it fades into darkness. But when you try to apply that same clarity to the Milky Way, everything becomes complicated. We cannot photograph our galaxy from outside. We cannot see its spiral arms laid out before us. We are embedded within it, looking across the disk, and what we see is not a neat structure but a confusion of near and far, bright and faint, obscured and revealed. The contradiction is this: the Milky Way should have a clear extent, a measurable size, just like other galaxies. But from our position inside it, that extent is maddeningly difficult to define. Every method of measurement gives a slightly different answer. Every definition of where the galaxy ends leads to a different boundary. This is not because the measurements are wrong or the definitions arbitrary. It is because galaxies, including our own, do not have hard edges. They fade gradually. The density of stars decreases smoothly with distance from the centre. The gas thins. The dark matter halo extends far beyond the visible stars, its influence weakening but never quite ceasing. From outside, this gradual fading is less problematic. You can choose a surface brightness level and say, the galaxy extends to where the light drops below this threshold. But from inside, where you are trying to measure distances to individual stars and reconstruct the overall shape, the gradual fading becomes a source of uncertainty. Another layer of contradiction comes from dust. When you look toward the galactic centre, toward the constellation, Sagittarius, where the Milky Way is brightest, your view is blocked by immense clouds of interstellar dust. The very heart of the galaxy, the region you most want to see to understand its structure, is hidden from optical telescopes. You can see the glow of stars on this side of the dust, and you can infer what lies beyond, but you cannot see through. This means that the most luminous part of the Milky Way, the central bulge containing billions of stars, is largely invisible to us in visible light. Infrared and radio observations can penetrate the dust, revealing what lies beyond. But the contradiction remains. The brightest region is hidden, the faint outer regions are difficult to detect, and we are left trying to map the whole from partial glimpses. The contradiction also appears in the different components of the galaxy. The disk has a measurable extent, perhaps 100,000 light-years across. The halo of old stars and globular clusters extends farther, perhaps twice that, the distance. The dark matter halo may reach 10 times farther still, hundreds of thousands of light-years, perhaps even 1 million. Which of these defines the size of the Milky Way? The answer depends on what you are measuring and why. If you are interested in star formation, you focus on the disk. If you are studying galactic dynamics, you need to include the dark matter halo. If you are mapping the galaxy's gravitational influence, you must consider the full extent of mass, visible and invisible. This multiplicity of definitions means that when someone asks how far the Milky Way reaches, there is no single answer. The question itself contains hidden assumptions about what counts as the galaxy, what you are measuring, and where you draw the line between inside and outside. The contradiction is also temporal. We see different parts of the galaxy at different times in the past. Light from the galactic center, 27,000 light-years away, shows us what was happening there 27,000 years ago. Light from stars in the outer disk, 80,000 light-years away, shows us their state 80,000 years ago. We are not seeing a snapshot of the galaxy as it is now, but a composite of different moments, all arriving simultaneously. This temporal contradiction complicates efforts to understand the galaxy's current structure. Stars move, gas flows, the spiral arms rotate. The galaxy we see is not frozen in a single instant, but spread across tens of thousands of years of history. For most purposes, this is not a significant problem because galactic structures change slowly, but it is another reminder that our view is always partial, always mediated by distance and time. Perhaps the deepest contradiction is this. We know more about the structures of distant galaxies millions of light-years away than we do about the full extent of our own. We can photograph Andromeda from outside and see its spiral arms clearly. We can measure its size, count its stars, map its gas. But the Milky Way, our home, remains partly mysterious because we cannot step outside to look. This irony is not lost on astronomers. The galaxy we should know best is in some ways the hardest to study. Proximity is both an advantage and a limitation. We can see individual stars in the Milky Way, study them in detail, measure their compositions and ages, but we cannot see the forest for the trees. The overall structure eludes us in ways that external galaxies do not. The contradiction teaches humility. It reminds us that knowledge is perspective dependent. What you can see depends on where you stand. The clarity we have about distant galaxies comes from distance, from the ability to see them whole. The confusion we face with the Milky Way comes from intimacy, from being embedded within what we are trying to understand. As you rest now, feeling your body grow heavy, think about this contradiction. The Milky Way is both known and unknown, both measured and mysterious. We live inside it, surrounded by its stars, breathing air made from its gas, built from atoms forged in its supernovae. And yet we cannot see it whole. We cannot step back and say, there, that is my galaxy, that is where it ends. The contradiction is not a failure of science, but a recognition of limits. Some questions are hard to answer, not because we lack tools or intelligence, but because the question itself is shaped by our position. We are inside the thing we are measuring, and that changes everything about how we measure it. And perhaps that contradiction is appropriate. Perhaps it is fitting that our home remains partly mysterious, that the place we know best is also the place we can never fully see. The Milky Way surrounds us, envelops us, defines the space in which we exist, and from that position we reach outward, trying to understand, trying to measure. Accepting that the view will always be incomplete, but striving nonetheless to know how far our galaxy truly reaches. As astronomers grappled with the challenge of measuring the Milky Way from within, different theories emerged about where the galaxy ends. Each theory was based on evidence, on measurement, on reasonable assumptions, but each led to different conclusions about the galaxy's extent. The disagreements were not about stubbornness or error. They were about the fundamental difficulty of defining a boundary for something that fades gradually, rather than stopping sharply. One early theory focused on the visible disk. The spiral arms, traced through young stars and gas clouds, clearly extended only so far. Beyond a certain radius, star formation ceased, the gas thinned, and the luminous structures that defined the disk disappeared. By this measure, the Milky Way was about 100,000 light-years across, perhaps slightly larger. This was a clean definition. It focused on the part of the galaxy that was most clearly structured, most actively forming stars, most visibly part of the spiral system. For many purposes, this was a useful boundary. Maps of the Milky Way often showed the disk extending to this limit, with the spiral arms curling out to about 50,000 light-years from the centre. But this definition excluded much. Beyond the visible disk lay the halo, a roughly spherical distribution of old stars and globular clusters. These objects clearly belonged to the Milky Way. They orbited the galactic centre, moving in wide loops that carried them tens of thousands of light-years above and below the disk. Their presence demonstrated that the galaxy extended far beyond the bright spiral arms. A second theory, therefore, defined the boundary by the halo. Globular clusters, some of the oldest objects in the galaxy, orbit at distances exceeding 100,000 light-years. The farthest known clusters lie more than 200,000 light-years from the centre. If you include these in your measurement, the Milky Way is at least twice as large as the visible disk. This definition made sense from a dynamical perspective. The globular clusters were gravitationally bound to the Milky Way. They orbited the centre just as the Sun did, though on much longer timescales and more elongated paths. They were part of the system, even if they were not part of the disk. Including them expanded the galaxy's reach significantly, but even this was not the full extent. Observations of how stars and gas moved at different distances revealed something puzzling. Objects far from the centre moved faster than they should, if only visible matter were present. This flat rotation curve, as it was called, suggested the presence of additional mass, invisible but real, extending well beyond the visible structures. This invisible mass became known as dark matter. Its presence was inferred from gravitational effects, from the motions of stars and gas that could not be explained by the mass of visible matter alone. If dark matter existed, and if it formed a halo around the galaxy as theory suggested, then that halo might extend hundreds of thousands of light-years, perhaps even a million. A third theory therefore defined the boundary by the dark matter halo. This definition was based not on light but on gravity, on the region within which the Milky Way's mass dominated. Estimating the extent of the dark matter halo was difficult because it could not be seen directly, only inferred from its effects. But models suggested it was vast, dwarfing the visible galaxy. Different astronomers favoured different definitions depending on their research focus. Those studying star formation worked with the disk. Those studying galactic dynamics included the halo. Those modelling the galaxy's gravitational influence incorporated dark matter. Each definition was valid for its purpose, but each gave a different answer to the question of how far the galaxy reached. The theories also diverged on the question of boundaries versus gradients. Some astronomers argued that the galaxy had a definable edge, a distance beyond which matter associated with the Milky Way became too sparse to count. Others argued that the galaxy faded gradually, with no sharp transition, and that any boundary was arbitrary, a convention chosen for convenience rather than reflecting physical reality. This philosophical divide ran deep. If galaxies had real edges, then they were discrete objects, separate from their neighbours. If they faded gradually, then they were more like clouds, blending into their surroundings, part of a continuum. The question was not just scientific, but conceptual. What does it mean for something to be bounded? Another theory emerged from studying satellite galaxies. The Magellanic Clouds, dwarf galaxies orbiting the Milky Way, clearly influenced and were influenced by our galaxy's gravity. Were they part of the Milky Way system, or were they separate? Their orbits carried them through regions that might be considered the outer halo. Their presence extend the Milky Way's reach, or were they simply neighbours? Streams of stars torn from the Magellanic Clouds and other satellites wrapped around the galaxy, connecting them to the main system. These streams blurred the boundary between what was the Milky Way and what was something else. If you included the streams, the galaxy's influence spread even farther. Some astronomers proposed defining the boundary by the virial radius, the distance within which the galaxy's gravity was strong enough to dominate over the expansion of the universe. This was a physics-based definition, tied to cosmology and the dynamics of structure formation. For the Milky Way, the virial radius was estimated at around 250,000 to 300,000 light-years, encompassing the dark matter halo and bound satellites. But this definition too was a gradient. The influence of gravity did not stop sharply at the virial radius. It faded gradually, weakening with distance but never, quite vanishing. In principle, every particle in the universe feels the Milky Way's gravity, however faintly. Drawing a line and saying beyond this is not the galaxy was always somewhat arbitrary. The theories multiplied as observations improved. gas surveys revealed that neutral hydrogen extended beyond the stellar disk, forming an outer gas disk that increased the measured size. Streams of gas connecting the Milky Way to the Magellanic Clouds suggested that the circumgalactic medium, a halo of hot diffuse gas, might extend hundreds of thousands of light-years. Each new observation added complexity. The Milky Way was not a simple disk but a layered system, each layer extending to a different distance. The theories evolved to incorporate this complexity, proposing different boundaries for different components while acknowledging that no single number could capture the full extent. As you breathe deeply now, let these competing theories wash over you. They are not contradictions, but perspectives, different ways of slicing the same reality. The Milky Way is large in many ways, and each way is true. The disk extends 100,000 light-years, the halo twice that, the dark matter halo perhaps 10 times farther, the gravitational influence even beyond. The theories remind us that the universe does not always yield simple answers. Sometimes the question is more complex than it first appears, and the answer depends on what you are asking and why. How far does our galaxy reach? As far as the stars, as far as the gas, as far as the dark matter, as far as gravity can hold. Each answer is correct. Each reveals a different aspect of our galactic home. Understanding where the Milky Way ends required more than speculation or theory. It required measurement, patient observation, and the development of techniques sophisticated enough to map structures we could not see directly. The pursuit of these measurements became one of the great ongoing projects of 20th and 21st century astronomy, drawing researchers from across the world, each contributing pieces to an increasingly detailed picture. The first challenge was measuring distances. Without knowing how far away stars and clusters were, astronomers could not determine the galaxy's extent. Early methods were crude, relying on assumptions about stellar brightness that often proved incorrect. But gradually, more reliable techniques emerged. Parallax, the apparent shift in a star's position as Earth orbits the Sun, worked well for nearby stars. By measuring the tiny angle of this shift, astronomers could calculate distance using simple geometry. But parallax only worked for stars within a few hundred light-years. Beyond that, the angles became too small to measure accurately with ground-based telescopes. The breakthrough came with Cepheid variable stars and RR Lyrae variables. These pulsating stars had a known relationship between their pulsation period and intrinsic brightness. Measuring how long they took to brighten and dim, astronomers could determine their true luminosity. Comparing that to their apparent brightness gave the distance. Henrietta Swan Leavitt discovered the period luminosity relationship for Cepheids in 1912 while working at Harvard College Observatory. Her discovery became the foundation for measuring cosmic distances, including distances within the Milky Way. By identifying Cepheids in globular clusters and in different parts of the disk, astronomers could map the three-dimensional structure of the galaxy. But even Cepheids had limits. They were bright enough to be seen across the galaxy, but dust absorption complicated the measurements. Starlight passing through interstellar dust became dimmer and redder, making stars appear farther away than they were. Astronomers had to develop correction factors, estimating how much dust lay between us and each star, adding uncertainty to every measurement. Radio astronomy provided a way around the dust problem. Gas clouds emit radio waves that pass through dust unaffected. By mapping the distribution of neutral hydrogen, which emits a characteristic 21 centimeter line, astronomers could trace the spiral arms even where optical light was blocked. Radio surveys revealed that the disk extended farther than optical observations suggested, with gas clouds marking the outer reaches of the spiral structure. The pursuit also required mapping the halo. Globular clusters, ancient spherical collections of hundreds of thousands of stars, orbit far above and below the disk. By measuring their distances and velocities, astronomers could determine how far out the halo extended and how much mass it contained. Harlow Shapley, despite being wrong about the nature of spiral nebulae, made crucial contributions to understanding the Milky Way's scale. In the 1910s, he used globular clusters as tracers of the galaxy's extent. He measured their distances using RR Lyrae variables and discovered that they formed a roughly spherical distribution around the galactic centre. Importantly, the Sun was not at the centre of this distribution. We were offset, about 2/3 of the way out from the core. This was another blow to human centrality, but it helped establish the galaxy's true size and our place within it. The pursuit intensified with space-based observations. The Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars with unprecedented precision. It extended the range of direct distance measurements tenfold, providing a solid foundation for understanding nearby structures. Then came Gaia, a European Space Agency mission that revolutionized the field. Launched in 2013, Gaia has measured the positions and motions of over 1 billion stars with extraordinary accuracy. Its data has allowed astronomers to map the Milky Way in 3 dimensions. Tracing spiral arms, identifying stellar streams, and revealing substructures in the halo. Gaia's precision is staggering. It can measure the position of a star to within micro-arc seconds, equivalent to seeing a coin on the moon from Earth. With such precision, parallax measurements extend across the entire galaxy. For the first time, astronomers could map the Milky Way's structure, not by inference but by direct measurement. The pursuit also involved tracking stellar motions. Stars orbit the galactic centre at speeds that depend on the mass contained within their orbits. By measuring these velocities, astronomers could infer the distribution of mass, including dark matter. The resulting rotation curves showed that the galaxy's mass extended far beyond the visible stars, providing evidence for a massive dark matter halo. Spectroscopy played a crucial role. By splitting starlight into its component wavelengths, astronomers could measure how fast stars were moving toward or away from us through the Doppler shift. Combined with proper motion measurements showing movement across the sky, this gave complete 3-dimensional velocities. Stars in the halo moved differently from those in the disk, revealing the structure and history of different components. Surveys multiplied. The Sloan Digital Sky Survey mapped millions of stars and galaxies, identifying faint halo stars and tracing streams from disrupted satellites. The 2-micron All-Sky Survey worked in infrared, penetrating dust to reveal stars near the galactic centre. Each survey added detail, filling in gaps, refining estimates. The pursuit was international. Observatories in Chile, Hawaii, Australia, Europe, and elsewhere contributed data. Radio telescopes like the Very Large Array in New Mexico and Parkes in Australia mapped gas distributions. Space telescopes like Hubble, Spitzer, and Chandra observed at wavelengths blocked by Earth's atmosphere, revealing hot gas, star formation regions, and high-energy phenomena. Computational power enabled new approaches. Simulations of galaxy formation could reproduce structures like the Milky Way, allowing astronomers to test whether their observations matched theoretical predictions. The simulations showed that galaxies grew through mergers, absorbing smaller companions over billions of years. This explained the streams of stars in the halo, remnants of past accretion events. The pursuit also required collaboration. No single observatory or researcher could map the entire galaxy. Teams formed around large surveys, sharing data, combining observations from multiple wavelengths, building consensus through collective effort. The picture of the Milky Way that emerged was not the work of one person, but of thousands, each adding measurements, each refining the map. Challenges remained. The galactic centre, 27,000 light-years away and hidden behind dense dust, was difficult to study in optical light. Infrared and radio observations revealed a crowded region with a supermassive black hole at its heart, but many details remained uncertain. The outer halo, sparse and faint, was hard to survey completely. New streams continued to be discovered, suggesting that more structure awaited detection. The dark matter halo presented its own difficulties. It could not be observed directly, only inferred from its gravitational effects. Models predicted it extended hundreds of thousands of light-years, but the exact distribution remained uncertain. Was it smooth or clumpy? Spherical or elongated? These questions required careful analysis of stellar and satellite motions. Another aspect of the pursuit involved studying our neighbours. The Magellanic Clouds, dwarf galaxies orbiting the Milky Way provided clues about our galaxy's mass and extent. Their orbits depended on the total gravitational pull, allowing astronomers to estimate how much mass the Milky Way contained. Streams of gas and stars connecting the clouds to our galaxy showed that interactions were ongoing. Andromeda, our nearest large galactic neighbour, offered a comparison. By studying Andromeda's structure in detail, astronomers could infer features of the Milky Way. If Andromeda had a halo extending far beyond its disk, the Milky Way likely did too. If Andromeda showed streams from disrupted satellites, we should look for similar features in our own halo. The pursuit continues even now. New instruments come online. New surveys begin. Each adds data. Each refines understanding. The James Webb Space Telescope, launched in 2021, observes in infrared, revealing stars and structures hidden by dust. Ground-based telescopes with adaptive optics achieve resolution rivaling space telescopes. Radio arrays with multiple dishes combine signals to create virtual telescopes thousands of kilometers across. As you rest deeply now, think of this pursuit as a long, patient quest. Not a single breakthrough, but centuries of accumulated effort. Each astronomer looking up, measuring, calculating, adding one more piece to the puzzle. The Milky Way slowly revealing itself through their collective work, through tools and techniques built on each other's insights. The galaxy does not yield its secrets easily. It hides behind dust, stretches across distances that take light thousands of years to cross, fades gradually into the space between galaxies. But the pursuit persists, driven by curiosity, by the desire to understand our home, by the recognition that measuring the galaxy's extent is also measuring our place in the cosmos. The work continues, the map grows clearer, and slowly, patiently, we trace the boundaries of our galactic home. After decades of theoretical debate and patient observation, the measurements began to solidify, not into a single definitive answer about the Milky Way's size, but into a rich dataset revealing different aspects of the galaxy's extent. The data came from multiple sources, each wavelength of light, and each observational technique adding layers to the picture. The stellar disk, the flat plane where most of the Milky Way's stars reside, showed clear patterns in the data. Surveys counting stars at different distances from the galactic centre found that the density dropped off steadily. Within 40,000 light-years of the centre, stars were relatively common. Beyond 60,000 light-years, they became sparse. By 80,000 light-years, the density had dropped to a small fraction of what it was in the inner disk. This gave a practical measure for the disk's extent. Most astronomers settled on a radius of about 50,000 light-years, making the disk roughly 100,000 light-years across. This was the bright spiral structure visible in photographs of similar galaxies, the region where star formation was active, where gas and dust concentrated, where the galaxy's visible mass resided. But the data showed more. The disk was not uniform in thickness. Near the centre, the stellar distribution was thicker, puffed up by the velocities of stars and the gravitational influence of the central bulge. Farther out, the disk thinned to only a few hundred light-years in height. Near the Sun, about halfway out from the centre, the disk was roughly 1,000 light-years thick, give or take. This thickness mattered for understanding how much of the galaxy we could see. Looking toward the galactic plane, we looked through the full thickness of the disk, seeing stars stacked in depth. Looking perpendicular to the plane, we quickly left the disk behind and could see through to intergalactic space or to other galaxies beyond. Gas extended farther than stars. Radio surveys mapping neutral hydrogen found that the gas disk continued beyond the stellar disk, reaching to perhaps 70 or 80,000 light-years from the centre. This extended gas disk was less dense than the inner regions, but it was still part of the galaxy, still bound by gravity, still contributing to the total mass. The data on globular clusters painted a different picture of extent. These ancient stellar systems orbited in the halo, and their distances had been measured carefully using RR Lyrae variables and other techniques. The nearest globular clusters lay only a few thousand light-years from the Sun. The farthest extended beyond 200,000 light-years. Omega Centauri, the largest globular cluster in the Milky Way, orbited at a distance of about 16,000 light-years. M15. Another prominent cluster lay about 33,000 light-years away. NGC 2419 was more distant still, orbiting at over 200,000 light-years from the galactic centre. Each cluster was a data point tracing the halo's extent. Counting all known globular clusters, about 150 had been catalogued. Though more likely existed hidden by dust near the galactic centre, or too faint to detect in the outer halo, their distribution was roughly spherical, confirming that the halo did not have the flattened shape of the disk, but enveloped the galaxy in all directions. The data on stellar streams added another dimension. Gaia's measurements revealed thin streams of stars wrapping around the galaxy, remnants of disrupted satellites. The Sagittarius stream, the most prominent, traced the path of the Sagittarius dwarf galaxy as it was torn apart by tidal forces. This stream looped around the Milky Way multiple times, its stars spread across more than 360 degrees of sky. Other streams were narrower. PAL 5, originating from the globular cluster Palomar 5, stretched for tens of thousands of light-years. GD1, another stellar stream, extended across a significant portion of the northern sky. Each stream provided data on the galaxy's gravitational field and the distribution of dark matter. The data on dark matter came from rotation curves. By measuring the velocities of stars and gas at different distances from the galactic centre, astronomers could infer how much mass was present. The results were clear. Visible matter, stars and gas combined, accounted for only about 1/10 of the total mass needed to explain the observed motions. The rest was dark matter. Models fitting the rotation curve data suggested that the dark matter halo extended to at least 200,000 light-years, possibly much farther. Some estimates placed the virial radius, the edge of the halo where the galaxy's gravity balanced the expansion of the universe, at around 250,000 to 300,000 light-years. But dark matter data was indirect, inferred rather than observed. The exact distribution remained uncertain. Was the halo perfectly spherical, or was it elongated? Was it smooth, or did it contain clumps and substructures? These questions affected estimates of the total mass and extent, but the data supported a massive invisible halo surrounding the visible galaxy. The circumgalactic medium, a halo of hot, diffuse gas, added more data. Observations of distant quasars showed absorption lines imprinted by gas surrounding the Milky Way. This gas extended to large distances, perhaps hundreds of thousands of light-years. It was too hot and diffuse to see directly, but its signature in quasar spectra confirmed its presence. Measurements of the Milky Way's total mass provided another constraint. By observing satellite galaxies orbiting the Milky Way and measuring their velocities, astronomers could estimate how much mass they were orbiting through. Current estimates suggested a total mass of about 1 to 1.5 trillion times the mass of the Sun, most of it in dark matter. This mass estimate had implications for the halo's size. To contain that much mass, the halo had to extend far beyond the visible stars. Models suggested a radius of at least 500,000 light-years for the full dark matter distribution, perhaps even larger. The Magellanic Clouds provided data through their orbits. These dwarf galaxies, at distances of about 160,000 and 200,000 light-years respectively, were clearly within the Milky Way's gravitational influence. Streams of gas, the Magellanic Stream and leading arm, connected them to our galaxy, stretching across more than 100 degrees of sky. These features showed that the Milky Way's reach extended at least to the orbits of the clouds. Comparing data from different sources sometimes revealed tensions. The mass estimated from globular cluster orbits did not always match the mass from stellar streams or from the rotation curve. These discrepancies drove refinement of models, improvement of measurements, and deeper understanding of the galaxy's complexity. One consistent finding across all datasets was the lack of sharp boundaries. Whether measuring stars, gas, globular clusters, or inferred dark matter, the density always decreased gradually with distance. There was no point where you could say definitively, beyond this, the Milky Way ends. Instead, Every component faded, thinned, blended into the space beyond. The data also revealed that the Milky Way was not perfectly symmetric. The disk showed warps and ripples, possibly caused by interactions with the Magellanic Clouds. The halo contained streams and structures, rather than a smooth distribution. The bar at the centre was elongated and rotating. These asymmetries reflected the galaxy's history, the mergers and interactions that had shaped it. As you breathe slowly, let the numbers fade into background. The data is precise, the measurements careful, the uncertainties quantified, but what remains is the essential picture. The Milky Way is a layered structure, a bright disk about 100,000 light-years across, a halo of stars and clusters extending twice that, a dark matter halo reaching perhaps 10 times farther, gas and gravitational influence extending farther still. Each layer is real, each measured, each contributing to the whole. The data does not give a single answer to how far the galaxy reaches, but it gives many answers, each true for what it measures. And from those answers, we build understanding. We trace the extent of our home. We map the space we inhabit. The data is the foundation, solid and tested, upon which all theories must build. All the measurements of stars and gas and clusters told a story about what we could see, but beneath and beyond those visible structures lay something else. Something that changed everything about understanding the Milky Way's extent. The hidden truth was dark matter, an invisible component that outweighed everything visible by a factor of 10 to 1, and extended far beyond the stars into regions we once thought were empty. The first hints came from rotation curves. In the solar system, planets farther from the Sun orbit more slowly. Mercury races around in 88 days. Neptune takes 164 years. This pattern follows, naturally, from gravity. The farther you are from the mass at the centre, the weaker the pull, the slower the orbit. Galaxies should follow the same pattern. Stars near the centre, where most of the mass is concentrated, should orbit quickly. Stars far out in the disk should orbit slowly. But when astronomers measured stellar velocities across the Milky Way, they found something unexpected. The rotation curve stayed flat. Stars far from the centre moved just as fast as those closer in. This should not be possible with only the visible mass. If stars and gas were all that existed, the rotation curve would drop off at large distances. The fact that it stayed flat meant additional mass was present, mass that could not be seen but whose gravitational pull was undeniable. Vera Rubin's work in the 1970s on other galaxies confirmed this was a universal phenomenon. Every spiral galaxy studied showed flat rotation curves. The conclusion was inescapable. Galaxies were embedded into halos of dark matter, invisible but massive, extending far beyond the visible structures. For the Milky Way, estimates of the dark matter halo size were staggering. If you included all the mass needed to explain the rotation curve and the orbits of satellite galaxies, the halo might extend to 500,000 light-years or more. Some models suggested distances exceeding 1,000,000 light-years, though at those scales the halo began to overlap with Andromeda's halo, making boundaries meaningless. The hidden truth meant that most of the Milky Way was invisible. When you looked up at the night sky and saw the band of the Milky Way stretching overhead, you were seeing only a small fraction of the galaxy's mass. The vast majority was dark matter, surrounding the visible structures like an invisible cocoon, holding everything together through gravity alone. What is dark matter? Despite decades of research, the answer remains elusive. It does not emit light, does not absorb light, does not interact with electromagnetic radiation in any detectable way. It makes itself known only through gravity, through its effects on the motions of visible matter. Candidates for dark matter include exotic particles left over from the Big Bang. WIMPs, weakly interacting massive particles, are a leading possibility. These hypothetical particles would pass through ordinary matter almost without interaction, detectable only through rare collisions in sensitive experiments. Despite years of searching, no direct detection has been confirmed. Axions, another candidate, are even lighter particles predicted by theories of particle physics. They too would interact very weakly with normal matter, making them extraordinarily difficult to detect. Other possibilities include primordial black holes formed in the early universe, or sterile neutrinos, hypothetical cousins of known neutrino particles. Whatever dark matter is, it shapes the galaxy fundamentally. Computer simulations of galaxy formation show that without dark matter, galaxies like the Milky Way would not exist. In the early universe, normal matter was too hot and diffuse to collapse quickly, but dark matter, unaffected by radiation pressure, began clumping together early. Its gravity created wells into which normal matter fell, forming the first stars and galaxies. The Milky Way formed within a dark matter halo. The visible galaxy, the stars and gas we see, is like foam on the surface of a deep ocean. The ocean itself, the dark matter, is far more massive and extends far deeper. This inverts our usual picture. The stars are not the main component. They are just the visible tip of something much larger. The hidden truth also affects how we think about boundaries. If most of the galaxy's mass is dark matter, then the edge of the galaxy is not where the stars fade, but where the dark matter halo blends into intergalactic space. And that transition is even more gradual than the fading of starlight. Dark matter density decreases smoothly with distance from the center. There is no sharp cutoff, no boundary where it suddenly stops. The halo fades into the cosmic web, the filaments of dark matter connecting galaxies across the universe. In this view, galaxies are not isolated islands but nodes in a network connected by invisible threads. The hidden truth changes the question of how far the Milky Way reaches. If you measure only what you can see, the answer is 100,000 light-years or so. If you include dark matter, the answer is 5 to 10 times larger. The difference is not a matter of better measurement, but of recognizing what counts as the galaxy. This realization was revolutionary. It meant that astronomy, the science of light and observation, had discovered something that could not be observed directly. Dark matter was real but invisible, present but undetectable, except through inference. It challenged the assumption that seeing is believing, and forced a more sophisticated understanding of evidence. The hidden truth also has implications for the future. When the Milky Way and Andromeda collide in about 4 billion years, it will not just be their stars and gas that merge. Their dark matter halos will merge too, blending into a single enormous halo surrounding the combined galaxy. In fact, the halos are already interacting, already beginning to overlap, long before the visible disks will meet. This means the collision has already begun in a sense. The invisible components of the galaxies are already feeling each other's gravity, already influencing each other's motions. The boundary between the two galaxies is not clear because their dark matter halos fade gradually and intermingle at the edges. As you sink deeper into rest, let this hidden truth settle gently. Most of what exists is invisible. Most of the Milky Way cannot be seen with any telescope, at any wavelength. It is there nonetheless, holding the galaxy together, shaping its structure, extending its reach far beyond the stars. The hidden truth is that home is larger than it appears, that what you see is only the surface, that beneath and beyond lies a vast invisible architecture. This truth does not diminish the visible beauty of the Milky Way. The stars still shine, the spiral arms still curve gracefully, the galactic center still glows. But now we know that all of this floats within something larger, something we can sense but not see, something that makes the galaxy what it is. The hidden truth expands our understanding, deepens the mystery, reminds us that the universe contains more than our senses reveal. And in that recognition lies a kind of wonder, knowing that the invisible is no less real than the visible, that darkness can shape light, that what we cannot see defines what we can. The discovery of dark matter and the recognition that galaxies lacked sharp boundaries triggered a fundamental shift in how astronomers thought about galactic structure. This was not just a matter of adding new data or refining measurements. It was a change in the conceptual framework itself, a paradigm shift that redefined what it meant to ask how far a galaxy reaches. Before this shift, galaxies were thought of as discrete objects with definable sizes. Like planets or stars, they had boundaries where one thing ended and another began. The Milky Way was a system of stars, gas, and dust arranged in a disk and halo, and somewhere out there was an edge where the galaxy stopped and intergalactic space started. This view was intuitive and practical. It allowed galaxies to be catalogued, measured, and compared. Astronomers could say Galaxy A is this large, Galaxy B is that large, and make meaningful statements about their relative sizes. The model worked well enough for many purposes, but the accumulating evidence challenged this neat picture. Dark matter extended far beyond visible structures. Gas halos surrounded galaxies at enormous distances. Satellite, galaxies orbited in regions that might or might not be considered part of the main galaxy. Tidal streams connected systems that were supposed to be separate. The boundaries, when examined closely, dissolved into gradients. The paradigm shift was recognizing that galaxies are not bounded objects but systems of nested components, each with its own characteristic scale, each fading gradually into the surrounding space. The Milky Way is not a single structure with one size but a collection of components. The disk, the bulge, the stellar halo, the dark matter halo, each extending to different distances, each contributing to the whole. This shift changed how questions were asked. Instead of asking, where does the Milky Way end, astronomers began asking, how far does the disk extend? How far does the halo reach? Where does the dark matter dominate? Where does gravitational influence fade? Each question had a different answer, and all the answers were part of understanding the galaxy's full extent. The shift also changed how comparisons were made. When comparing the Milky Way to Andromeda or other galaxies, it became important to specify what was being compared. Disk size, total stellar mass, dark matter halo extent, these were different measures that could give different rankings. Andromeda might be larger in disk size but similar in total mass, or vice versa, depending on how measurements were made. This complexity was not a failure of science but a recognition of reality. Galaxies are complex systems, and simple comparisons can be misleading. The paradigm shift acknowledged this complexity and developed frameworks to handle it. Another aspect of the shift involved thinking about edges as transitions rather than boundaries. In the old paradigm, an edge was where something stopped. In the new paradigm, an edge was where one regime transitioned to another, where density dropped below a threshold, where one component faded and another became dominant. Edges were not walls, but gradients, not lines, but zones. This had profound implications for cosmology. If galaxies faded gradually, then the space between them was not empty but filled with diffuse matter, the intergalactic medium. Galaxies were not islands but nodes in a network, connected by filaments of gas and dark matter forming the cosmic web. The universe was more continuous than discrete, more connected than isolated. The paradigm shift also changed how galactic evolution was understood. Galaxies did not grow by accretion at well-defined edges, but by gradual accumulation across their entire extent. Gas flowed in from the circumgalactic medium. Small satellites were absorbed into the halo. Dark matter halos merged before visible structures touched. Growth was a continuous process spread across the galaxy's full reach, not a discrete addition to a fixed core. This understanding came from simulations as much as observations. Computer models of galaxy formation, which included dark matter and gas, dynamics, showed how galaxies built up over billions of years. The simulations reproduced structures like the Milky Way, with disks, bulges, halos, and satellites, all emerging naturally from initial conditions in the early universe. The simulations also showed that what we call the Milky Way today was assembled from hundreds or thousands of smaller systems that merged over time. Each merger added mass, created streams, and reshaped structures. The galaxy was not built once but continuously, and it was still growing, still accumulating material from its surroundings. The paradigm shift was uncomfortable for some. The old framework, with its clear boundaries and definable sizes, was simpler and more satisfying. The new framework, with its gradients and nested scales, was messier and harder to communicate. But it was also more accurate, better reflecting the reality of what observations revealed. For the public, the shift was harder to grasp. When asked how big the Milky Way is, people wanted a single number, a simple answer. But the true answer was more nuanced. It depends on what you mean by the Milky Way, what component you are measuring, and where you draw the line. This complexity was frustrating but honest. The shift also affected how astronomers thought about the Milky Way's future. The collision with Andromeda, predicted for about 4 billion years from now, was not a sudden event but a gradual process already underway. The dark matter halos were already overlapping. Gas was already being exchanged. The merger would unfold over billions of years, with the galaxies passing through each other multiple times before finally settling into a single system. In the new paradigm, asking when the merger would occur was less meaningful than asking when different stages would happen. When would the disks first pass through each other? When would the black holes merge? When would star formation peak? Each stage was part of a continuum, not a discrete moment. The paradigm shift extended beyond the Milky Way to all galaxies. Every spiral, every elliptical, every dwarf showed similar patterns. Gradual fading, dark matter dominance, nested components. The framework developed for understanding the Milky Way applied universally, showing that our galaxy was not special but representative of a common type. As you rest deeply now, feeling the weight of your body sinking into stillness, let this shift wash over you. The universe is more complex than simple categories suggest. Galaxies are not objects with clear edges, but systems with layered structures, each layer extending to different distances, each component contributing to a whole that defies easy measurement. The paradigm shift is a reminder that understanding evolves. What seemed clear becomes complicated as observations improve. But complications bring deeper truth. The Milky Way is richer, more extensive, more intricately connected than anyone imagined. And in recognizing that complexity, we come closer to grasping what our galaxy truly is, how far it reaches, and what it means to call it home. When the paradigm shift occurred, when astronomers fully grasped that galaxies lacked sharp boundaries and that most of their mass was invisible dark matter, the effects rippled outward through the entire field of astronomy. What had seemed like settled questions reopened. Techniques that worked under old assumptions needed revision. And the very language used to describe galaxies had to adapt. The first ripple affected how observations were conducted. If dark matter dominated galactic mass, then studying galaxies required techniques that could detect its gravitational influence, not just its visible light. Spectroscopy, measuring the velocities of stars and gas, became essential for every major galactic study. Rotation curves, once a specialized topic, became fundamental data needed to understand any galaxy's true extent. For the Milky Way specifically, this meant a surge of surveys measuring stellar velocities. Projects like RAVE, the Radial Velocity Experiment, and later Gaia's spectroscopic component, measured millions of stars, building a three-dimensional map of not just where stars were but how they moved. This motion data revealed the gravitational field, and from that, the distribution of all mass, visible and dark. Another immediate ripple was methodological. The old approach of counting stars to determine galactic size was no longer sufficient. You also needed to measure gas distributions, trace halo structures, model dark matter halos, and account for satellites and streams. Multidisciplinary collaboration increased. Optical astronomers worked with radio astronomers. Infrared specialists teamed with X-ray observers. Theorists partnered with observers to interpret the data. The ripple affected funding and telescope time allocation. Proposals to study dark matter or map galactic halos, once considered niche topics, became central to understanding galaxies. New instruments were designed specifically to address these questions. Radio arrays for mapping hydrogen gas, infrared telescopes for seeing through dust, spectrographs for measuring velocities, all became priorities. Educational curricula changed too. Astronomy textbooks had to be rewritten. The chapters on galaxies expanded to include sections on dark matter halos, rotation curves, and the difficulty of defining boundaries. Students learned that galaxies were more complex than earlier generations had been taught, that the simple picture of a disk of stars was incomplete. The ripple also affected how research was organized. Large surveys became more common because mapping a galaxy's full extent required data from many objects. Single-target studies were still valuable, but understanding galactic structure required statistical samples, not just individual measurements. This drove the development of survey telescopes designed to observe large areas of sky efficiently. Gaia, which measured positions and velocities for over 1 billion stars, was the culmination of this trend. Its data revolutionized Milky Way studies, allowing astronomers to trace structures that had only been hypothesized before. Stellar streams, the warping of the disk, the motions of satellites, all became measurable with precision that previous generations could not imagine. The immediate ripple extended to public communication. Explaining the Milky Way's size became more difficult because the simple answer was no longer accurate. Science communicators had to convey that galaxies were layered systems, that size depended on definition, that most of the galaxy was invisible. This was harder to communicate than a single number, but it was more honest. Planetarium shows and science museums updated their exhibits. The Milky Way was no longer just a beautiful spiral in images. It was a complex system with components extending far beyond what could be photographed. Exhibits included rotation, curves, visualizations of dark matter halos, and explanations of how astronomers inferred what they could not see. Another ripple affected related fields. Cosmology, the study of the universe's origin and evolution, depended heavily on understanding dark matter. The paradigm shift in galaxy studies fed back into cosmology, refining models of structure formation and the nature of dark matter itself. Particle physics, searching for dark matter candidates, received input from astronomers about how much dark matter existed and how it was distributed. The ripple also affected how errors and uncertainties were treated. In the old paradigm, measuring a galaxy's size seemed straightforward, with errors coming from distance, uncertainties, or observational limits. In the new paradigm, systematic uncertainties from modelling assumptions became more important. How you modelled the dark matter halo affected your estimate of the galaxy's extent, and those models had their own uncertainties. This meant that published measurements of the Milky Way's mass or size came with larger error bars, not because observations were worse, but because the problem was more complex. Honest assessment of uncertainty became more important, and astronomers had to communicate that some questions did not yet have definitive answers. For collaboration across disciplines, the ripple was profound. Astronomers studying the Milky Way now needed to understand cosmology, particle physics, and fluid dynamics in addition to traditional observational astronomy. The boundaries between subfields blurred. Galactic astronomy became inseparable from cosmology and high-energy physics. International cooperation increased. Mapping the Milky Way required observations from both hemispheres, access to multiple telescopes, and sharing of data across borders. Projects like Gaia were inherently international, with teams from dozens of countries contributing. The ripple effect was a more connected, collaborative approach to research. The shift also rippled into technology development. If dark matter could not be observed directly, new ways to detect its effects were needed. Gravitational lensing, the bending of light by mass, became a powerful tool. By observing how light from background galaxies was distorted as it passed near the Milky Way's halo, astronomers could map the dark matter distribution. This drove development of wide-field imaging surveys that could detect faint gravitational distortions. It also motivated research into new detectors, more sensitive instruments, and better data analysis algorithms. The technological ripple from the paradigm shift was as significant as the scientific one. Another immediate effect was on the study of satellite galaxies. Understanding the Milky Way's extent required understanding what orbited within it. The Magellanic Clouds, dwarf spheroidals, and streams from disrupted satellites all provided constraints on the halo's size and mass. This made satellite studies central rather than peripheral to understanding the Milky Way. Surveys for new satellites intensified. Fainter and fainter dwarfs were discovered orbiting in the outer halo, each one adding a data point for modelling the galaxy's gravitational field. By the 21st century, dozens of satellites were known, compared to only a handful in the 20th century. The ripple extended to adjacent fields like astrobiology. If galaxies were larger than previously thought, if they contained more dark matter and extended farther into space, did that change estimates of habitability? The circumgalactic medium, the outer reaches of the disk, these regions were now recognized as parts of the galaxy. Could they host life? Or were they too sparse, too energetic, too far from the processes that enriched gas with heavy elements? As you breathe slowly, completely relaxed, let these ripples fade into the background. The immediate effects of the paradigm shift were practical, concrete changes in how astronomy was done. New observations, new collaborations, new ways of thinking. The shift did not just change ideas, it changed practice, transforming the field from within, and those changes continue to shape how we study the Milky Way, how we measure its extent, how we understand our place within it. The paradigm shift that recognized galaxies as gradient systems with invisible halos did not just affect immediate research. Its echoes reverberated through the decades, reshaping entire subfields and influencing how astronomy itself was taught and practiced. The long-term impact was as significant as the initial breakthrough, perhaps more so, because it changed not just what we knew, but how we approached the cosmos. One of the deepest echoes was in cosmology. Understanding that galaxies were embedded in dark matter halos transformed how astronomers thought about the universe's large-scale structure. The cosmic web, that vast network of filaments and voids stretching across billions of light-years, was not primarily made of stars or gas, but of dark matter. Galaxies formed where filaments intersected, where dark matter was densest. This realization connected galactic astronomy to cosmology in ways that had not existed before. Studying the Milky Way's halo was not just about one galaxy, but about testing theories of how structure formed in the universe. The properties of our halo, its mass, its distribution, its substructures, all constrained models of cosmology extending back to the early universe. The echoes reached back to the Big Bang itself. Dark matter must have existed in the first moments of the universe, before any stars formed, before any galaxies assembled. Its properties affected how matter clumped, how fast structures grew, how the cosmic microwave background looked. Understanding the Milky Way's dark matter halo meant understanding something fundamental about cosmic history. Another long-term echo affected the philosophy of science. The acceptance of dark matter, something that could not be observed directly, but only inferred, challenged the empiricist tradition that valued direct observation above all. Dark matter was real not because anyone had seen it, but because its effects were undeniable, and no alternative explanation worked as well. This philosophical shift had implications beyond dark matter. It opened the door to considering other aspects of the universe that might be real but unobservable. Dark energy, the mysterious force accelerating the universe's expansion, gained acceptance more easily because astronomers had already learned to accept the invisible. The paradigm set by dark matter prepared the way for other revolutionary ideas. The echoes also affected how science was communicated. The Milky Way became a poster child for the limits of perception. Here was something surrounding us, something we lived within, yet most of it was invisible. This became a powerful metaphor. Educators used it to teach that reality extended beyond what our senses revealed, that knowledge came through reasoning as much as observation. In popular culture, dark matter captured imaginations. Science fiction writers incorporated it into stories. Films and television shows referenced it. The public became familiar with the idea that most of the universe was made of something mysterious we could not see. This cultural echo spread the impact far beyond astronomy. The long-term echo in astronomical instrumentation was profound. Entire classes of telescopes and detectors were developed to study dark matter's effects. Gravitational wave observatories, though designed primarily to detect colliding black holes, could also potentially reveal information about dark matter. Underground experiments searched for dark matter particles directly. The quest to understand dark matter drove technology across multiple disciplines. For education, the echoes meant that training astronomers required broader knowledge. Students had to learn about particle physics to understand dark matter candidates. They needed cosmology to understand halo formation. They needed computational skills to run simulations. The field became more interdisciplinary, and the echoes of the paradigm shift shaped what counted as essential knowledge. The echo also affected how data was archived and shared. Understanding the Milky Way required combining observations from many sources across many wavelengths over many years. This drove development of astronomical databases and data sharing protocols. Gaia's data, for instance, was made publicly available, allowing researchers worldwide to contribute to Milky Way studies. The culture of open data, now standard in astronomy, was partly a response to the need for comprehensive datasets to understand complex systems like galaxies. Another long-term effect was on citizen science. Mapping the Milky Way's structure involved identifying streams, finding faint satellites, and classifying structures in massive datasets. These tasks were well suited to crowdsourcing. Projects like Galaxy Zoo and others engaged the public in scientific research, democratizing astronomy in ways that echoed the paradigm shift's recognition that galaxies were more complex than experts alone could easily map. The echoes reached into how the Milky Way was visualized. Artist conceptions evolved from simple spiral disks to layered images showing the visible disk surrounded by ghostly halos of dark matter. These visualizations helped communicate the new understanding, but they also shaped how even scientists thought about the galaxy. The images became tools for thought, not just illustrations. The long-term impact on understanding galactic evolution was perhaps the most scientifically significant echo. Recognizing that galaxies grew through mergers, absorbing satellites and building up their halos, transformed theories of galaxy formation. The Milky Way was not pristine but assembled, not original but composite, built from hundreds of smaller systems over billions of years. This history was written in the streams and chemical compositions of halo stars. Each stream told a story of a past merger. Each metal-poor star hinted at origins in the early universe. The echoes of ancient collisions literally surrounded us, embedded in the structure of the galaxy we call home. The paradigm shift also echoed into the search for extraterrestrial life. If galaxies were larger and more complex than previously thought, with vast halos and circumgalactic media, did that change where we should search? Were the outer regions of galaxies habitable, or was life confined to the disk? These questions remained open, but the framework for asking them had changed. For understanding the future, the echoes were equally important. When the Milky Way merges with Andromeda, it will not just be the visible disks that combine, but the dark matter halos. The resulting galaxy will have a halo built from both, potentially extending even farther. The paradigm shift provided the tools to model this future, to predict what the merged galaxy would look like billions of years from now. As you rest deeply, think of these echoes as waves spreading outward from a stone dropped in water. The initial splash was the paradigm shift, the recognition that galaxies were more than they appeared, but the waves spread far, touching cosmology, particle physics, philosophy, education, technology, culture. The echoes continue even now, shaping research, inspiring questions, guiding the search for understanding. The Milky Way, once thought to be a simple disk of stars, revealed itself through these echoes as a vast complex system, most of it invisible, extending far beyond what anyone imagined. And that revelation, that paradigm shift, echoes through time, changing not just what we know about our galaxy, but how we think about the universe itself. Behind every measurement of the Milky Way's extent, behind every map of its structure, behind every theory about its boundaries, there are people. Individuals who devoted years or decades to understanding a question that has no simple answer, who looked up and refused to accept mystery as the final word, who built instruments and developed methods to probe the invisible. Think of Harlow Shapley, working in the early 20th century, counting globular clusters and realizing they formed a spherical distribution around a point far from the sun. His measurements were tedious, requiring photographic plates exposed for hours, careful measurements of star positions, calculations done by hand or with mechanical calculators. He discovered that the sun was not at the center of the galaxy but displaced to one side, about 2/3 of the way out. This single realization reshaped our understanding of our place. Shapley's work required patience. Each globular cluster had to be studied individually, its distance estimated, its position mapped. There were no shortcuts, no computers to speed the calculations, just night after night at the telescope, day after day, analysing plates, year after year, building the picture piece by piece. His dedication was driven by curiosity, by the desire to know, by the recognition that understanding the Milky Way's size was understanding humanity's place in the cosmos. Consider Henrietta Swan Leavitt, whose discovery of the period luminosity relationship for Cepheid variables became the foundation for measuring cosmic distances. She worked at Harvard College Observatory as one of the women computers, human calculators who measured photographic plates and recorded data. The work was repetitive, the pay was low, the recognition minimal. Yet from this tedious labour came one of the most important discoveries in astronomy. Leavitt noticed that Cepheid variables with longer periods were intrinsically brighter. This relationship, once calibrated, allowed distances to be measured across vast reaches of space. Without her work, mapping the Milky Way's extent would have been far more difficult. She died in 1921 without seeing the full impact of her discovery, without knowing that her patient observations of variable stars would reshape our understanding of the universe. Think of Vera Rubin, who in the 1970s measured rotation curves of galaxies and found the evidence for dark matter. She faced skepticism, both for her measurements and for her conclusions. Some colleagues suggested errors in her data, others proposed alternative explanations. But she persisted, refining her techniques, gathering more observations, building an overwhelming case. Rubin's work required not just technical skill, but courage. She was challenging the prevailing understanding of galaxies, suggesting that most of their mass was invisible. That was not an easy position to defend, but the evidence was clear, and she had the conviction to present it despite resistance. Her contributions fundamentally changed how we think about galaxies, including our own. Consider also the engineers and technicians who built the instruments these astronomers used, the telescope makers who ground mirrors to precise curves, the spectrograph designers who split light into its component wavelengths, the computer programmers who wrote software to analyze data. Each contributed their skills, their expertise, their dedication to the collective effort. Jan Oort, the Dutch astronomer, spent decades mapping the Milky Way's structure using radio observations. He traced the spiral arms by mapping neutral hydrogen gas, penetrating the dust that blocked optical light. His work showed that the galaxy was larger and more complex than earlier optical studies suggested. He lived through the Nazi occupation of the Netherlands during World War II, continuing his work despite hardship, driven by the belief that understanding the cosmos mattered even in dark times. Think of the Gaia mission team, hundreds of scientists and engineers from across Europe and beyond, who spent decades designing, building, launching, and operating a space telescope dedicated to mapping the Milky Way. The mission required solving extraordinary technical challenges, measuring stellar positions to within micro-arc seconds, tracking over 1 billion stars simultaneously, maintaining stability in the harsh environment of space. The team included optical designers, software engineers, data analysts, project managers, each playing a role. The mission's success was not the work of one genius, but of many skilled people collaborating, solving problems together, sharing data, building on each other's insights. The map of the Milky Way they produced is a collective achievement, a testament to what humans can accomplish when working toward a common goal. There are also the graduate students who spent years on dissertation projects, measuring distances to globular clusters, tracing stellar streams, or modelling dark matter halos. Many of their names are not famous, but each added pieces to the puzzle. Each night at a telescope, each data analysis session, each published paper contributed to the growing understanding. Think of the observers who spent cold nights at mountain observatories, guiding telescopes, monitoring instruments, ensuring that data were collected properly. Observational astronomy requires patience and discomfort. Telescopes work best on high mountains where the air is thin and the nights are cold. Observers work through the night, staying awake when their bodies want to sleep. maintaining focus when fatigue sets in. The dedication required is substantial. An observer might travel to an observatory for a week, work every clear night, and if clouds intervene, have little to show for the effort. Yet they return again and again, because the data matter, because understanding the Milky Way requires these observations, because the quest to know drives them forward. Consider the theorists who built computer simulations of galaxy formation, modelling how dark matter halos grew, how gas collapsed into disks, how satellites merged with larger galaxies. These simulations required years of work, developing code, testing algorithms, running calculations on supercomputers, comparing results to observations. The theorists were dreamers in a different way, imagining processes on scales of billions of years, translating physical laws into equations, and from equations into digital universes. Volker Springel, Julio Navarro, Simon White, and many others developed simulations that reproduced galaxies like the Milky Way, showing that the observed structures could emerge naturally from cosmological initial conditions. Their work connected the small-scale, individual galaxies to the large-scale, the cosmic web. It showed that understanding the Milky Way meant understanding its place in cosmic history. There were also the skeptics, those who questioned each new claim, demanded better evidence, proposed alternative explanations. Their role was essential too. Science advances not just through bold ideas, but through rigorous testing. The skeptics kept the field honest, ensuring that conclusions were based on solid evidence, that uncertainties were acknowledged, that alternative possibilities were considered. Think of the librarians and archivists who preserved astronomical data, the journal editors who peer-reviewed papers, the conference organizers who brought researchers together. Each played a supporting role, maintaining the infrastructure that allowed science to progress. Without them, the individual contributions of observers and theorists would not have accumulated into collective knowledge. The human element reminds us that understanding the Milky Way is not an abstract process, but a deeply human endeavor. People chose to dedicate their lives to this question. They faced challenges, overcame obstacles, worked together, competed with each other, shared ideas, and built knowledge collectively. The map of our galaxy that we now have is their achievement, the result of countless hours of work by countless individuals. And the work continues. New astronomers take up the quest, armed with better instruments, standing on the foundations built by earlier generations. They ask new questions, probe deeper, refine understanding. The Milky Way still holds mysteries, still challenges those who try to measure it. And those challenges continue to attract dreamers, people who look up and wonder, who refuse to accept limits, who push toward greater understanding. As you breathe slowly now, think of these dreamers scattered across time and space, from Shapley in the 1910s to the Gaia team in the 21st century, from observers on cold mountain nights to theorists at computer screens, from those whose names are famous to those whose contributions are anonymous. Each looked at the same galaxy, each asked how far it reached, each added something to the answer. You are connected to them through the knowledge they built. When you look up at the Milky Way, you see not just stars, but the result of their efforts. The understanding we have, imperfect as it is their gift. They measured the immeasurable, mapped the invisible, traced the boundaries of a home we cannot leave. They were dreamers, and their dreams became knowledge, became understanding, became the answer, however complex, to the question of how far our galaxy truly reaches. For every measurement claiming to define the Milky Way's extent, there were skeptics questioning the methods, doubting the conclusions, proposing alternatives. This opposition was not obstruction but an essential part of how science works. Truth emerges not from consensus but from the grinding process of claim and counterclaim, evidence and critique, hypothesis and test. When Shapley proposed that the Milky Way was far larger than previously thought, placing the Sun tens of thousands of light-years from the centre, not everyone agreed. Some astronomers questioned his distance estimates to globular clusters, suggesting his methods overestimated how far away they were. If the clusters were closer, then the galaxy was smaller, and the Sun might still be near the centre. The debate was technical. Shapley used RR-Lyrae variables to measure distances, assuming they all had similar intrinsic brightness. But what if some were brighter than others? What if dust absorption made them appear fainter, leading to overestimated distances? These were legitimate concerns, and they had to be addressed with better observations and refined calibrations. The opposition forced Shapley to strengthen his case. He measured more clusters, checked his calibrations against other methods, accounted for dust as best he could. The process was slow, but it produced more reliable results. The opposition did not stop him. It made his conclusions more robust. When evidence for dark matter emerged from rotation curves, the opposition was fierce. Many physicists and astronomers resisted the idea that most of a galaxy's mass could be invisible. The claim seemed extravagant, almost absurd. Surely there was a simpler explanation. Some proposed that the rotation curves were measured incorrectly, that systematic errors in spectroscopy were creating the illusion of flat rotation. Others suggested that our understanding of gravity might be wrong at galactic scales, that Newton's and Einstein's laws needed modification. Modified Newtonian dynamics, or MOND, gained supporters who argued that adjusting gravitational physics was more parsimonious than inventing invisible matter. This opposition drove decades of additional research. Rotation curves were measured more carefully, with better instruments, in more galaxies. The results consistently showed the same pattern. MOND, while elegant in some ways, struggled to explain all observations. It worked for rotation curves but failed to account for gravitational lensing or the cosmic microwave background. The weight of evidence tilted toward dark matter, but the opposition kept proponents honest, forced them to consider alternatives, prevented premature certainty. The question of where the Milky Way ended also sparked debates. Some astronomers argued that the galaxy should be defined by its luminous matter, the stars and gas, making it about 100,000 light-years across. Others insisted that the dark matter halo was part of the galaxy, extending its reach to hundreds of thousands of light-years. Still others proposed defining the boundary by gravitational dominance or by the virial radius. Each definition had defenders, and each led to different sizes. The debates were not just semantic, but reflected deeper questions about what counted as a galaxy. What made something part of a system versus separate from it? These were philosophical as much as scientific disputes, and they lacked definitive resolution. Instead, the community learned to accept multiple definitions, each useful for different purposes. There was also opposition to the idea that galaxies lacked sharp boundaries. Some astronomers found the notion of gradients and fuzzy edges unsatisfying. They wanted clear demarcations, definable limits. The idea that you could not point to a boundary and say, "Here the galaxy ends," went against intuition and tradition. This opposition manifested in debates at conferences, in skeptical peer reviews of papers, in grant proposals questioned or rejected. The opposition was not monolithic but distributed, coming from different individuals for different reasons. Some opposed specific measurements, others opposed theoretical frameworks, still others opposed the philosophical implications. Yet over time, the evidence accumulated. Observations from multiple independent sources converged on similar conclusions. The rotation curves were real. Dark matter was necessary. Boundaries were gradients. The opposition gradually softened, not because skeptics were defeated, but because evidence became overwhelming. This process took decades. In the 1970s, dark matter was controversial. By the 1990s, it was widely accepted. In the 2000s, it became standard. The opposition did not disappear entirely. Small groups still propose alternative theories, but the mainstream moved on, incorporating dark matter into models and using it as a framework for further research. Another battle involved the Milky Way's total mass. Early estimates were too low, placing the galaxy at a few 100 billion solar masses. As observations improved, the estimates grew. By the early 21st century, estimates ranged from 1 to 1.5 trillion solar masses, with most of that in dark matter. But different methods gave different answers, and the uncertainties were large. Some astronomers argued that the Milky Way was less massive, others that it was more massive. The debate hinged on technical details: how you modelled the halo, what assumptions you made about its shape, which satellite orbits you included in your analysis. Each choice affected the result, and different researchers made different choices. The opposition here was methodological. It was not about rejecting dark matter, but about determining how much was present and how it was distributed. This type of opposition is healthy, pushing researchers to be more careful, to test their assumptions, to explore how sensitive their conclusions are to modelling choices. There were also disputes about specific features. When streams of stars were discovered wrapping around the galaxy, some astronomers questioned whether they were really streams or just chance alignments of unrelated stars. The skeptics demanded better evidence, clearer demonstrations that the stars move together, tighter constraints on their orbits. This opposition led to more detailed observations, better statistical analyses, stronger conclusions. The battle for truth was never a single conflict, but a series of skirmishes fought over decades across multiple fronts. Each measurement, each theory, each claim about the galaxy's extent faced scrutiny. Some withstood the scrutiny and became accepted. Others were modified, refined, or abandoned. This process, contentious as it was, produced reliable knowledge. The Milky Way's structure, as we understand it today, is built on measurements that survived skepticism, on theories that explained observations better than alternatives, but on conclusions tested and retested until confidence was warranted. The opposition also kept the field from becoming complacent. No measurement was final, no theory beyond question. There was always room for refinement, always possibility that new observations would reveal something unexpected. This humility, born from opposition, kept astronomy honest. As you rest now, think of this battle not as conflict for its own sake, but as a process for finding truth. The opposition asked hard questions, demanded better evidence, proposed alternatives, and in answering those challenges, in addressing those concerns, astronomers built stronger foundations for understanding. The Milky Way's extent is known not because everyone agreed easily, but because claims were tested rigorously, because skepticism was answered with evidence. Because the battle for truth, though slow and sometimes frustrating, ultimately led to understanding that could be trusted. There comes a moment in understanding when something shifts from intellectual knowledge to felt awareness. You can know facts about the Milky Way, memorize numbers, understand concepts, but truly grasping what it means to live in a galaxy without clear boundaries, to be surrounded by invisible matter extending far beyond what you can see, that requires a different kind of comprehension. An awakening. The awakening often begins with scale. You can read that the Milky Way is 100,000 light-years across, but understanding what that means is different. Light takes 100,000 years to cross the galaxy. The starlight you see from the far side of the disk left its source during the last ice age, when early humans were learning to control fire, when the landscape of Earth was unrecognizable compared to today. Every photon carries that history. When the light entered your eyes, it had been travelling longer than human civilization has existed. That journey is not an abstraction but a physical reality. The light is old, ancient, carrying information from a time before anyone looked up and wondered about the stars. The awakening deepens when you consider position. The Sun orbits the galactic centre at about 828,000 kilometers per hour. That seems fast. Impossibly fast. Yet at that speed, it takes about 225 million years to complete one orbit. In all of human history, we have not completed even a fraction of a single lap around the galaxy. This means that the constellations we see, the positions of stars relative to each other, have barely changed during all of recorded history. The sky our ancestors saw was essentially the same sky we see, but on galactic timescales, everything is in motion, everything is changing. We simply do not live long enough to notice. Another dimension of awakening involves recognizing the invisible. Most of what surrounds us is dark matter. You cannot see it, cannot touch it, cannot detect it directly, yet it is there, holding the galaxy together, extending far beyond the stars, comprising most of the mass within which we live. The galaxy is mostly invisible, and we are embedded in that invisibility like swimmers in an unseen ocean. This recognition changes perception. When you look at the night sky, you are not seeing the galaxy. You are seeing a tiny fraction of it, the part that happens to emit light. The full extent surrounds you in every direction, unseen but real, stretching hundreds of thousands of light years beyond the farthest stars you can detect. The awakening also comes from understanding gradients. There is no edge to the Milky Way, no boundary where it stops. It fades gradually, density decreasing smoothly with distance. This means that asking where you are in relation to the galaxy becomes complicated. You are definitely inside the disk, clearly within the halo, probably within the dark matter distribution. But where exactly inside is less clear because inside has no sharp definition. This lack of boundaries can be unsettling. We are used to thinking of objects as bounded, as having insides and outsides. But the galaxy is not bounded. It is a gradient, a fading, a transition into something else. You belong to it not because you are inside a container, but because you are part of a system held together by gravity, moving with billions of other stars in orbital patterns shaped by the collective mass. The awakening is also emotional. Some feel smallness, recognizing that our entire existence is a speck within a structure so vast that light takes millennia to cross it. Others feel connection, realizing that everything around us, from the atoms in our bodies to the stars above, is part of the same system, shaped by the same history, bound by the same forces. Both responses are valid. The Milky Way is so large that human scale becomes almost meaningless. Yet we are capable of understanding that scale, of measuring it, of comprehending our place within it. That capacity is itself remarkable, a form of reaching that transcends physical size. Another aspect of awakening involves temporal awareness. The galaxy has existed for more than 10 billion years. It formed in the early universe, grew through mergers, continues to evolve. Our lives are brief flickers in that vast span. The galaxy was here long before us and will continue long after. Yet in this moment, we are part of it, participants in its ongoing story. This perspective can bring calm. The stresses and anxieties of daily life, though real and important on human scales, are tiny ripples on a much larger surface. The galaxy does not care about human concerns, but recognizing that can paradoxically provide comfort. We are small, yes, but that smallness removes pressure. We do not carry the weight of the cosmos. We simply exist within it. The awakening also includes recognizing motion. The galaxy is not static but rotating, with different parts moving at different speeds. The sun orbits, carrying us with it. Other stars orbit on their own paths. The whole structure is dynamic, changing, though so slowly that we perceive it as fixed. In reality, the galaxy is a dance, billions of stars in coordinated motion shaped by gravity. Knowing this changes how the night sky feels. The stars are not painted on a dome but moving through space, each on its own trajectory. Some are approaching us, others receding. The galaxy is alive with motion, and we are part of that motion, one dancer among billions. Another layer of awakening comes from understanding connections. The Milky Way is not isolated but part of the local group, gravitationally bound to Andromeda and smaller neighbours. Its dark matter halo overlaps with Andromeda's. Gas flows between systems. The boundaries between galaxies are fuzzy, blended, interpenetrating. We belong not just to one galaxy but to a system of galaxies, to a network extending across millions of light years. This recognition expands the sense of home. Home is not just the Milky Way, but the local group. And the local group is part of the Virgo supercluster, and that is part of Laniakea, and so on, each scale of structure embedded in the next. Home expands the farther out you look, until it encompasses the observable universe itself. The awakening is not a single moment but a gradual process. Each new piece of understanding adds to it. Each contemplation deepens it. You might read about the galaxy's size and feel nothing. Then one night, look up and suddenly feel the weight of that knowledge, the reality of the vast invisible structure surrounding you. As you breathe deeply now, let this awakening touch you gently. You live in a galaxy without edges, surrounded by invisible matter, moving through space at hundreds of thousands of kilometers per hour, part of a structure that has existed for billions of years and will continue long after you are gone. The galaxy is both immense and intimate, both distant and immediate. You cannot see most of it, but it shapes everything about your existence, from the atoms in your body to the orbit of your planet. The awakening is recognizing that you are part of something vast. That the question of how far the galaxy reaches is also a question about the extent of home, and that home has no clear boundary, but fades gradually into the cosmic dark. This awareness does not change the physical reality, but it changes how you experience it. The night sky becomes more than stars. It becomes the visible edge of an invisible immensity, and you, in this moment, are awake to that truth. After exploring the measurements, the theories, the debates, the human effort behind understanding the Milky Way's extent, we arrive at the deepest truth. It is not a number, not a measurement in light years, not a count of stars or calculation of mass. The deepest truth is that asking how far our galaxy reaches is really asking something more fundamental about the nature of boundaries, belonging, and what it means to call something home. The revelation is this. The Milky Way teaches us that boundaries are human constructs, useful for certain purposes, but not fundamental to nature. Galaxies do not end. They fade. The transition from inside to outside is gradual, not sharp. There is no line where you can say definitively, beyond this point is not the Milky Way. This truth applies at every scale. The disk fades into the halo. The halo fades into the dark matter distribution. The dark matter fades into the intergalactic medium. The circumgalactic gas blends with filaments of the cosmic web. At no point is there a wall, a membrane, a surface that marks the limit. Instead, there are gradients, transitions, regions where one thing becomes less concentrated and another becomes more prominent. This reveals something profound about the universe. Nature prefers continuity over discreteness. It creates gradients, not boundaries. What we call edges are conveniences, definitions we impose to make sense of continuous variation. But the variation itself is the reality, and it does not stop at any single point. The revelation extends to identity. If the Milky Way has no clear edge, then what makes it the Milky Way? What defines it as a distinct entity? The answer is not location, but relationship. The galaxy is a system of matter, bound together by gravity, moving in coordinated patterns, sharing a common history. The stars, gas, dark, matter, all of it belongs to the Milky Way because it participates in that system, not because it resides within defined borders. This is a different way of thinking about belonging. You belong to the galaxy not because you are inside a container, but because you move with it, because you are part of its gravitational system, because your atoms were forged in its stars and will one day return to its interstellar medium. Belonging is dynamic, not spatial. The deepest truth also involves recognizing what the question, how far does our galaxy reach, actually asks. On the surface, it is a question about distance, about measurement, but beneath that, it is a question about extent of influence, about where home stops and elsewhere begins, about the limits of the system we are part of. And the answer, when you look closely, is that the limits are soft, negotiable, dependent on what you are measuring and why. If you are studying star formation, the disk is what matters. If you are modelling gravity, the dark matter halo is essential. If you are thinking about the future merger with Andromeda, then the overlapping halos define a shared region that belongs to both galaxies or to neither. Each answer is correct for its context. The revelation is not that one answer is right and others wrong, but that the question contains multiplicities, that the galaxy is large in many ways simultaneously, and that recognizing this multiplicity is itself a form of understanding. Another layer of the revelation involves accepting uncertainty. Even after centuries of observation, the Milky Way's extent is not precisely known. Estimates of its mass vary by factors of 2 or more. The dark matter distribution is inferred but not directly observed. The far reaches of the halo are too faint to survey completely. New streams continue to be discovered, suggesting more structure awaits detection. This uncertainty is not a failure. It is a recognition of complexity. The galaxy is not a simple object that can be fully catalogued. It is a dynamic system, constantly evolving, with features at many scales. Understanding it completely may be impossible, and accepting that impossibility is part of the revelation. The deepest truth also touches on time. The galaxy you see is not the galaxy that exists. Light takes time to travel, so different parts appear at different moments in their history. The center you observe is 27,000 years old. Distant halo stars appear as they were hundreds of thousands of years ago. There is no single present moment for the galaxy, only a collection of pasts arriving simultaneously. This means that the galaxy's extent is not just spatial but temporal. How far it reaches depends on when you are measuring. The galaxy has been growing through mergers, accumulating satellites, expanding its reach. In the future, it will merge with Andromeda, and the question of how far the Milky Way reaches will become meaningless, because it will no longer exist as a separate entity. The revelation includes recognizing that the galaxy is mortal. It has a history, a present, and a future that will transform it. The structure we know, the spiral disk with its arms and bulge, is temporary. In 4 billion years, it will be gone, replaced by something new. The galaxy is not eternal but a phase, a stage in an ongoing process. And yet, despite its impermanence, despite its lack of boundaries, despite the uncertainty and complexity, the Milky Way is real. It exists. You are part of it. The revelation is not that everything is vague or unknowable, but that reality is richer than simple categories suggest. The galaxy is both knowable and mysterious, both measured and immeasurable, both defined and indefinable. The deepest truth is that asking how far our galaxy reaches opens into questions about the nature of systems, boundaries, and belonging. It shows that the universe does not divide neatly into separate things, but exists as a web of relationships, gradients of density, flows of matter and energy. The Milky Way is one node in that web, one concentration in a vast continuum, and we, living within it, are participants in that continuum. We are made of the galaxy's matter, shaped by its history, moving in its gravitational field. The extent of the galaxy is, in some sense, the extent of our own origins, our own belonging. To ask how far it reaches is to ask how far home extends, and the answer is that home fades gradually into the larger universe, but never entirely disappears. As you rest now, completely relaxed, let this revelation settle without effort. The Milky Way is vast and intimate, bounded and boundless, knowable and mysterious. It is a galaxy among billions, yet it is your galaxy, the one that holds your world. Its reach is measured in hundreds of thousands of light years, and in the beating of your heart, in the motions of stars and in the atoms of your breath. The deepest truth is that the galaxy does not end. It transitions, it fades, it blends into the cosmos, and in that fading, in that lack of boundaries, lies a profound lesson about the nature of existence itself. We have journeyed through the history of measuring the Milky Way, through the challenges of observing from within, through the discovery of dark matter and the recognition that boundaries fade rather than stop. Now, as we near the end of this exploration, it is time to pause and reflect on what it all means, not just scientifically, but humanly, personally, existentially. What does it mean to know that you live in a galaxy without clear edges? It means accepting that home is not a container with walls, but a gradient, a fading concentration of matter held together by gravity. It means recognizing that belonging is not about being inside defined borders, but about participating in a system, moving with it, being shaped by it. This challenges the usual way we think about place. On Earth, places have boundaries. Cities have limits, nations have borders, properties have fences. We are used to knowing when we are inside something and when we are outside, but the galaxy offers no such clarity. You are inside it, but there is no moment when you cross a boundary and enter. You simply are part of it, have always been part of it, because you exist within its gravitational system. What does it mean that most of the galaxy is invisible? It means that reality extends beyond perception, that what we can see is only a fraction of what exists. This is a humbling recognition. Our senses evolved to navigate a world of light and solid objects, but the universe contains much that lies beyond those senses. Dark matter, forming most of the galaxy's mass, cannot be seen or touched, only inferred through its effects. This teaches a kind of humility about knowledge. We can understand things we cannot observe directly. We can infer structure from motion, deduce presence from absence. Science extends our senses through instruments and reasoning, but it also teaches us that the visible world is not the whole world. Most of what exists is hidden, and we must accept that incompleteness while still striving to understand. What does it mean that the galaxy is so vast? It means that human concerns, however important they feel, exist on a scale almost infinitesimally small compared to the cosmic structures we inhabit. The galaxy is 100,000 light-years across, has existed for over 10 billion years, contains hundreds of billions of stars. Our lives are measured in decades, our history in thousands of years, our entire species a recent arrival in the galaxy's long story. This perspective can diminish, making human life seem insignificant, or it can liberate, removing the burden of cosmic importance and allowing us to simply exist, to experience, to create meaning on the scales we actually inhabit. The galaxy does not care about human affairs, but that indifference is not hostile. It is simply beyond the scale, where care makes sense. What does it mean that we can understand the galaxy despite living within it? It means that consciousness, whatever it is, has the remarkable property of reaching beyond immediate experience. We cannot leave the galaxy, cannot photograph it from outside, cannot touch its far reaches, yet through observation, reasoning, and imagination, we can map it, understand its structure, trace its history. This capacity is itself extraordinary. A creature that lives for decades can comprehend a structure that exists for billions of years. A mind housed in a few pounds of biological tissue can model systems stretching across light years. This reaching, this ability to understand what we cannot directly experience, is one of the defining characteristics of human intelligence. What does it mean that the galaxy will one day merge with Andromeda? It means that nothing is permanent, not even structures as vast as galaxies. The Milky Way as we know it is temporary, a phase in an ongoing process of cosmic evolution. In 4 billion years, it will be part of something larger, transformed beyond recognition. The spiral arms will be gone, the disk disrupted, the identity dissolved. This impermanence extends to everything. Stars are born and die, planets form and are destroyed, even atoms, over incomprehensible timescales, may decay. Nothing lasts forever. But this is not a tragedy. It is simply the nature of a dynamic universe. Change is not decay, but transformation. One form becoming another. Continuity through variation. What does it mean that we are made of the galaxy's matter? It means that the boundary between self and galaxy is not absolute. The atoms in your body were forged in stars, scattered in supernovae, gathered into new stars and planets. You are not separate from the galaxy, but a temporary configuration of its matter, a pattern that will one day dissolve and return to the interstellar medium. This connection is profound. You are not in the galaxy as a passenger in a vehicle. You are of the galaxy, made from it, shaped by it, destined to return to it. The calcium in your bones, the iron in your blood, the carbon in your cells, all were created in stellar cores and ejected into space. You are literally made of stardust, and when you die, those atoms will continue, recycled into new forms. What does it mean that the galaxy extends so much farther than we can see? It means that the night sky, beautiful as it is, shows only a tiny fraction of our home. The dark matter halo, the circumgalactic medium, the faint outer halo, all of these components surround us invisibly. The galaxy is far larger, far more extensive, far richer than the band of light stretching overhead suggests. This hidden extent reminds us that appearances can be deceiving. What looks modest or contained may actually be vast. The faint blur of the Milky Way in the sky is the visible edge of a structure extending hundreds of thousands of light years in all directions. Most of it is dark, silent, invisible. But it is there, holding everything together, shaping the space we inhabit. What does it mean to live in the suburbs of a galaxy? The sun orbits about 2/3 of the way out from the centre, in a relatively calm region. We are not in the dense, crowded core where stars pass close and radiation is intense. We are not in the sparse outer reaches where heavy elements are scarce. We are in a middle zone, sometimes called the galactic habitable zone, where conditions allow for stable planetary systems and the chemistry of life. This location is not random. Life as we know it requires certain conditions, and those conditions are met more easily in regions like ours. Too close to the centre, and stellar encounters might disrupt planetary orbits. Supernova explosions might sterilize worlds with radiation. Too far out, and there might not be enough heavy elements to form rocky planets. We live where we do because here, the conditions allowed us to exist. What does it mean that the question of how far the galaxy reaches has no single answer? It means that reality resists simple categorization. The universe does not conform to our need for clean definitions. The Milky Way is 100,000 light-years across if you measure the disk. Twice that if you include the stellar halo. 10 times that if you include dark matter. Each answer is true, each incomplete, each useful for different purposes. This multiplicity of answers is not confusion but richness. The galaxy is complex, layered, multifaceted. Understanding it requires accepting that complexity, holding multiple perspectives simultaneously, recognizing that the question itself contains assumptions that shape the answer. Wisdom is not finding the one true answer, but understanding how different answers relate to each other. As you breathe deeply, completely at rest, ponder these meanings gently. The Milky Way is your home, vast and invisible, ancient and evolving, knowable and mysterious. It surrounds you in ways you cannot see, extends beyond what you can imagine, connects you to cosmic processes spanning billions of years. To understand how far it reaches is to understand something about the nature of place, of belonging, of what it means to exist in a universe where boundaries fade and continuity prevails. We have travelled far through this long night, from ancient observations of a mysterious band in the sky to modern measurements of dark matter halos extending hundreds of thousands of light-years. We have explored the challenges of measuring a galaxy from within, the discovery that most of its mass is invisible, the recognition that boundaries are gradients rather than lines. Now, as our journey concludes, it is time to return to where we began, to the simple act of looking up. The legacy of understanding the Milky Way's extent is not just scientific knowledge, but a transformed perspective. We now know that the faint band arching across the sky is the cross-section of an immense structure, that we live embedded within something far larger than we can see, that our home extends not just to the visible stars, but to invisible halos, reaching into the space between galaxies. This knowledge changes how the night sky feels. When you look up and see the Milky Way, you are not just seeing stars. You are seeing the edge of a system that surrounds you completely, that extends in all directions, that holds you in its gravitational embrace. The visible band is a window into your own neighbourhood, a view along the plane of the disk you inhabit. The legacy includes the tools and methods developed to map the galaxy. Parallax measurements, spectroscopy, rotation curves, surveys of millions of stars, computer simulations, each technique built on earlier work, each generation of astronomers adding refinements. The methods that revealed the Milky Way's structure are now applied to other galaxies, helping us understand galactic evolution across the universe. The legacy also includes the human effort, the dedication of countless individuals who spent careers measuring what seemed unmeasurable, who refused to accept that living within the galaxy meant we could never understand it. Their persistence, their ingenuity, their collaboration across generations produced the knowledge we now have. We stand on their shoulders, seeing farther because they built the foundations. But perhaps the deepest legacy is the recognition that home is larger and stranger than we imagined. The Milky Way is not just 100,000 light-years of stars, but hundreds of thousands of light years of dark matter, gas, and gravitational influence. It is not a bounded object, but a fading concentration, not separate from the universe, but part of a continuum. Home does not end at a boundary. It gradually blends into the cosmic background. This recognition is both humbling and comforting. Humbling because it shows how small we are, how brief our existence compared to the galaxy's long history. Comforting because it shows we are part of something vast, connected to structures and processes that extend far beyond our individual lives. We belong to the galaxy not despite our smallness, but because of it. We are one small part of an enormous whole. The return to looking up is not a return to ignorance, but to wonder informed by knowledge. You can stand beneath the night sky now, see the Milky Way stretched overhead, and know what you are seeing. Not just stars scattered randomly, but a disk viewed edge-on, with spiral arms, a central bulge, an invisible halo. You can know that you are moving through this structure at hundreds of thousands of kilometers per hour, that the stars are in motion too, that the whole galaxy is a dynamic system constantly evolving. You can know that most of what surrounds you is invisible, that the dark matter halo extends far beyond the farthest stars, that asking where the galaxy ends is asking a question with no single answer. And yet, despite that complexity, despite the lack of boundaries, despite the invisible components, you can still look up and feel that you are home, that you belong, that this vast structure is the place you call yours. The closing is not an ending, but a return enriched by understanding. The question of how far our galaxy reaches has been explored from many angles, through history and measurement, through theory and debate, through the human effort to know and the scientific recognition of limits. What remains is the essential truth that the Milky Way is both knowable and mysterious, both measured and immeasurable. The legacy for future generations is the knowledge we have built and the questions that remain. We know more about the Milky Way than any previous generation, yet mysteries persist. What is dark matter? How exactly did the galaxy form? What structures await discovery in the faint outer halo? Each generation will push understanding farther, refine measurements, discover new features. The quest continues. The return to looking up also means accepting that the simple question, how far does our galaxy reach, opens into complexity. The answer depends on definition, on what you measure, on what you count as the galaxy. The disk extends 100,000 light years, the stellar halo twice that, the dark matter halo perhaps 10 times farther. Each answer is correct. Each reveals a different aspect of our home, and perhaps that is fitting. Home should be complex, layered, richer than any simple description. The Milky Way is all of those things. It is the bright disk we can see and photograph. It is the halo of ancient stars and clusters. It is the invisible dark matter holding everything together. It is the gas flowing in and out. It is the satellites orbiting at the edges. It is all of these at once, simultaneously, a system of nested structures, each with its own scale. As you return now to the present moment, feeling your body at rest, your breathing slow and steady, carry with you this knowledge. You live in a galaxy that extends far beyond what you can see, that has no clear edge, that fades gradually into the space between galaxies. You are part of it, made from it, moving with it. The question of how far it reaches is also the question of how far home extends, and the answer is that home is both contained and boundless, both near and incredibly distant. The night sky remains, waiting for you whenever you look up. The Milky Way will be there, patient and unchanging on human timescales, slowly evolving on cosmic ones. And now you know what you are seeing. Know that the band of light is a galaxy viewed from within. Know that it extends far beyond what your eyes can detect. Know that you belong to it in ways both profound and mysterious. Thank you for travelling through this exploration tonight. If you found peace in these reflections, if the vastness brought calm rather than anxiety, if the journey helped you rest, then perhaps you will return to these questions again. The Milky Way will always be there, always extending outward, always fading into the dark, always reminding us that home is larger than we imagine, and that understanding, however incomplete, is worth pursuing. Sleep well beneath the stars. Dream of galaxies and time, of invisible halos and gradual boundaries, of home that has no edge but continues, fades, blends into the cosmos. And when you wake, remember that you carry the galaxy with you, that its atoms form your body, that its history shapes your present, that asking how far it reaches is also asking how far you belong. The answer is written in starlight and dark matter, in measurements and mysteries, in the patient work of those who looked up and wondered. The galaxy reaches as far as gravity holds, as far as matter extends, as far as home can be imagined, and that, in the end, is farther than any single number can express.